And Howard, I don't know if we're live yet, but if we are, Howard Bucket says, "Hold on, guys. She's taking her time to look her best for me." I love that. That's pretty awesome. So let me check to see whether or not we are actually live, and oh, looks like it's going live now. Okay, so I may have to say that again. I'm looking at myself right at the moment. I see that we are live. Yeah, so I caught the Howard. I want to make sure, Howard, you actually heard what I said. So I see myself on there. Looks like you got it. It's good. And how's my audio today? Is it good? Hopefully everything is cool in that regard. I got a new mic, and it doesn't fit the pack, the battery pack that I have, so I had to send it back. So I'm using my bad mic, which has a short in it. So what I've done is I've taped the pardon my language, holy hell out of this microphone. So hopefully it won't short out. But if it does, I am a recording studio. I do have other alternatives, so I have another mic. So what I need to be sure of is to make sure that if this mic, this lavalier mic, goes out at any point during this broadcast and I don't catch it, scream at me through the chat, because I've got it up on the TV, and I will pick up my secondary mic and I will talk through the show with with this one. So this one will not fail. So at any rate, I've got all this stuff. And for those of you who actually have my cell phone number, feel free to call and say, "Tamitha, your mic went out." So we don't have any more of those crazy 17-minute broken mini course things. That was so embarrassing. Anyway, okay. So audio, excellent, excellent, wonderful. Let's hope it stays that way. Like I said, you'll know because this will get all staticky. It'll be like kind of sounding like there's, like I'm frying bacon in the background. So feel free again to give me a call, give me a text. Probably call is better. My number is on. So if I get a phone call in the middle of this, I will know what it's for. Okay. So hello, everybody. I see everyone's having a good time this morning. I read through the chat, and everybody's very relaxed, and which is perfect mood. I mean, you guys have set the mood perfectly for today, because today is going to be a lot more about storytelling than it is about heavy mental, machinations. We are in the storytelling mode when it comes to solar flares and radio bursts. And for those of you who are in my Patreon, my mini course patrons, mini course patrons on this side, and I apologize if I haven't added your name yet. That will get on this list, I promise. I've gotten a few new people who have joined and a few people who've dropped off. I appreciate, by the way, if you have to drop off for any reason, don't worry about it. Drop off, come back, that kind of thing. I know sometimes money gets tight. It's definitely a case with me. So I just appreciate anything you guys do to help make these things possible. You're also helping fund the development of these courses for the Millersville University Graduate Certificate Program. And as an update, I am this close to becoming an adjunct professor. I've had my last interview. It looks like we're finalizing things, so very soon, maybe the next time you see me, I will actually be an adjunct professor at Millersville. So we're going to start getting the ball rolling for space weather broadcasting. Then also I wanted to say for the, let's see, am I doing it the right way now? My big thanks to the VIP steering committee. These guys are actually helping me create some of these courses. We're having very in-depth discussions regarding things like health and safety. What do we worry about in terms of medical for humans, or for let's say the airlines? How do we approach issues that we have with some of these effects, space weather effects, when it comes to things like airlines and emergency radio and all of this stuff. So my debt of gratitude to all of these VIP members who really help steer the ship, and I just couldn't do it without all of you, honestly, and I'm just very, very grateful. So a Mr. Microphone. No, this is not a Mr. Microphone. For those of you in the audio world, this is a Shure Beta 52. And it's a very standard dynamic mic that people use for singing, usually vocals, when it's got a bubble top like this. So it's good because then I can wave it all around and it's not going to pick up everything else. So these are really good mics for that. So at any rate, yes, I actually work in audio, so I know what I'm doing, believe it or not. Okay, let's see. Any opening questions really fast before I jump in? I will say, oh, thank you, congratulations, professor. Yes, I have never been a professor, and I will actually now be one, even though people have called me a professor for years. I have never been an official professor in a university, so this is kind of a nice little perk. Not all doctors are professors, by the way. So, hi from the UK and hi from Ireland and everywhere. Thank you, you guys. So this is, to get to the class, this is the third installment. And for you, those of you on Patreon, I told you that this is the third and final installment of solar flares and radio bursts. And I hate to say it, I lied. Because as I put this course together, I ended up with like 49 charts. And I'm like, oh God, that's way too much. So, and the reason why I did 49, I have 49 charts, is because I'm going to go into these things in detail. As a matter of fact, I might as well go to the first slide. I'm going to go into, where can I stand? Yes. Into all of this in detail. Let me get way over here. Make sure I'm out of the words here. We have gone through flare dynamics. We have gone through radio bursts, what they are, and I'll give a slight review so that we can kind of remember what the last two courses were. But for this course, we're going to be talking mainly about the effects, and I'm going to give very specific examples of these effects. And I really wanted to go into detail. And as I started going into detail, as a matter of fact, I'm going to be borrowing charts from other people's presentations that were given at Space Weather Week. These are Air Force presentations. These are obviously public presentations, but they are presentations from people who are leaders in the field in this kind of research, and I wanted to be able to use their stuff so that you can go offline, because a lot of these people have papers on their own, and I can put links in the description for where to find these papers, and I will also do it on Patreon. I'll actually put links to the actual papers themselves at Patreon, because this stuff is so important, and we're going to start seeing a lot more of this. And you'll notice that as I go through the examples, you'll see that boy, these effects were bad, but man, if they happen today, what would happen? I mean, because we are so reliant on things that just even 5 to 10 years ago we weren't. So as I started going into more and more detail on these actual events, I realized I'm just building up chart after chart after chart, and I'm just not going to be able to get through it. And I thought, well, let me just pare it down. And I said, no, then I'm going to miss some of the details. And I really want to be sure to give you the details because it's so very important. And plus, it's part of the Millersville training that I'm going to be giving the meteorologists that are getting the graduate certificate. They need to know this stuff in the level of detail that I'm going to present today. So, in effect, I lied. I'm going to do one more course. But I promised the last course, which will be the next one, that's when I'll go into the Carrington event again. You've already seen me go into the Carrington event. And as a matter of fact, if I can stand on this side for a second, you'll see a Carrington class. There's a 1959 and a 1972 Carrington class event. I've already gone through the 1959 one back when I did coronal mass ejections. So now we're going to talk a little bit about the effects from the solar radio burst, or from the solar flare side. There's not a lot of information, but I'll go through it a little bit. And then I'll talk about the other one that was a Carrington class event that happened in 1972. Now this is prior to GPS, but it's very similar to the 1959 event. And we have a lot more information, a lot more data on what the solar flare was like and the types of disruptions it caused. Back in 59, we didn't really have all that much in terms of even understanding that solar flares could cause radio blackouts and things like that. So we didn't have ways of measuring them. I think about 69, we started really doing that. But these are eras when we didn't even know that there was a solar wind. If you go back to one of my early courses, I think on CMEs, you'll see me go through the whole litany and the whole history of how we actually discovered the solar wind. And back during some of these events, these early Carrington events, we didn't even know that stuff yet. So really, a lot of what we know about these Carrington class events and about just these big solar bursts and things like that is really what we've learned in the space age. And as you can see, the amount of knowledge that we're getting is really beginning to make us realize how important space weather is. So, getting to it, like I said, I'll do a review, and then I'll go into the effects of the solar radio emission at Earth for the December 2006 event. This was a huge GPS disruption, the largest I think we have on record. you know, this is the only one that we have really for GPS since GPS has been invented. I mean, in terms of a really global scale disruption. And then I'll also talk about the 2017 September events, the radio burst during Hurricane Irma. We had Harvey, Irma, and Marie. I'll talk about some of the intense effects that we had and how badly amateur radio operators struggled, because there's some papers published on that as well. So that's going to be, really, believe it or not, that's going to be what we're going to be able to cover today, simply because there's just so much information. So is there any, I would love to hear your views on solar storms and the possible effect on humans and consciousness. Yeah, that's hard. There are a lot of humans who are susceptible to these things, but mostly more the geomagnetic storm side of things than, let's say, solar flares and radio bursts. So I won't go into that today. But there is a medical aspect, and more medical researchers are beginning to take note and do some serious studies, which is a good thing. Let me, before I get totally into this, let me run through the chat here really fast. I'll scroll back because I thought I saw a couple other questions. So let me just disappear off the screen for just a moment while I scroll back and take a look. Have I looked at Birkeland currents? Oh, here we go, the electromagnetic plasma currents. You know, the problem that we have looking at just the electric field is electric fields are very rapidly changing. They're very hard to measure. Anything that we've ever done to measure these currents have very high errors in them, because we have all sorts of things, and distortions and disruptions, plasma waves, all sorts of things that cause electric field measurements to be very, very difficult. So a lot of people end up measuring the counterpart of that, which is the magnetic field, because it's a lot easier to measure, and it's a lot less susceptible to, it's a lot easier to isolate and get decent measurements of the magnetic field. And it also doesn't wiggle nearly as much. So for mainstream science, I know that the fringe science is all into, no, it's all electricity, it's all electricity. Magnetism doesn't matter. And, you know, mainstream science goes, no, look at Maxwell's equations. They're tied together. And since electric current, you know, potentials and actual currents are a lot of times very difficult to measure without a lot of error, there's a whole huge camp of people that say, let's measure the magnetic field and deduce what the electric field should be. So yes, there's a lot of stuff that's done, especially in the ionosphere, regarding electric currents, but out in space plasmas and out around the Earth's magnetic shield, it's not an electric shield, it's a magnetic shield with electric currents on it. The electric currents are there to try to neutralize and alter the dynamics of the particles that are entering the shield. In order to study this, it ends up being a lot more robust going at it from the magnetic field point of view. So that's really the low-hanging fruit, and that's why you see mainstream science working more often with magnetic fields when it comes to big phenomena. Electric fields are looking more at particle kinetics. You see a lot of people look at electric fields for that. But there are different paradigms, but they're still related. And I think it's going to be a while before you're going to see people really trying to look at the global electric circuit, because it really couples down even into the neutral atmosphere, and we can't even get terrestrial meteorologists and ionosphere, thermosphere people to talk to each other yet. So let's try to get all these different disciplines to shake hands first before we try to solve a problem that requires all these disciplines to be shaking hands. That's really my take on it. So hopefully that answers the question regarding the electric universe and why I don't go into it. Okay, so let me do a little bit of a review. Actually, let me hang on a second. Let me slide this back down so I get the current chat. What do you think of the chemtrails? Oh gosh, guys, come on, give me a break. Can I talk about radio bursts? Any questions on radio bursts and solar flares instead of the electric universe and chemtrails? I'd kind of appreciate it. Okay, so let me review this really fast for you. We have, from the last couple courses, you've seen this plot. When we talk about the sun and we talk about solar radio bursts, we obviously have to go back to things like sunspots and the solar activity and the sources of them. But automatically makes us look at light, electromagnetic radiation from X-rays and gamma rays all the way down to radio waves, right? And sunspots have always been something that people kind of get confused about because they forget that sunspots emit multiple frequencies of light. Sunspots are visibly dark, as you can see here in this left-hand plot. If I can stand out of the way. The left-hand plot shows the sunspots and actually shows some solar flux measurements, and you can see when that sunspot goes by, that solar flux drops intensely and then comes back. Sunspots are dark in visible light, at f10.7 and in the wavelengths that actually reach the ground, and that's why they look dark when you look at them. However, if we go to the I think it's 1.4 gigahertz image, I think my caption is wrong. This is from the very large array, radio array. You can see all these bright spots are sunspots, but in 1.4 gigahertz, they're very bright. So what is dark in the visible range is actually very bright in radio. And as we got more into the science, we realized that, as you can see from this last image, the sunspot itself really still is dark, and that's where, that's what we look at. But really the radio source actually is above the sunspot. So here's a picture of the sunspot on the limb. You can actually see kind of the dark, if I scoot over a little bit more, you can see that dark region right there on the limb. That's the sunspot itself. So the sunspot's kind of rotating away from Earth view. And you can see this little white contour. That's the source of where the radio burst is coming from, or the radio noise. As we learned, that is actually from a loop, a magnetic loop that sticks out of the sun and is emitting all sorts of different types of radio noise. Now, as we continued going on, and I'll get back over here, as we continued going on, we realized that radio waves from the sun, and here we go in these different wavelengths again, that makes the sun look very different. And if we look at the sun in different wavelengths, we're actually looking at different heights in the solar atmosphere, we can see very different views of what the sun is doing. And we learned that the different frequencies of light, as you go up in the solar atmosphere, you go down in frequency. So, let's see if I've got it here. Come on, there we go. So, and I'll get to that more in a second. This is the plot I actually thought I was going to have up. If you guys recall, if we look at the standard model of a solar flare, and I'll flip on this side, we'll look at this first. You can see the sunspot down here at the base, right? Now this is all review again. You guys have already known this from the last couple courses. See the foot points there? Those are the sunspot foot points, and then you've got this magnetic loop that comes up, okay, that red loop, and it's sticking above the surface, and you even have a higher loop. You see this kind of weird light blue thing that wiggles through there. That thing is what is, on this side, what we call the CME that is going to be launched. So on this side of the models, as I'm looking down at my own notes here, or my visible, so I know where to point. You can see that loop here, right, that yellow loop, that ends up, as it's tethered in this structure, you've got the lower loops underneath, and you've got the higher loop that's kind of tethered, it kind of folds in and pinches. So you've got a loop that kind of folds in and pinches, and it's holding this yellow mass of material inside it in a big flux tube. That loop, as it pinches, it breaks, and as it breaks, the smaller loops fold back down, and this bigger loop erupts and flies out. And that's when I flip back over here, that's kind of what they're showing. You see that the red lower loop, you see that little tether, and you see the two arrows going like this. And as the big CME with this bigger loop flies off of the screen and out into the solar wind, the lower loop retreats down. You've got plasma shooting down the loops this way and plasma shooting up the loops this way, and you've got a whole host of radio emission that occurs. And when you do that when you look at that radio emission, the most high energy stuff like hard X-rays and microwave stuff, you got hard X-rays near the foot points, you got with slightly lower frequency stuff, the microwave stuff occurs kind of up here at the top of this loop and up into here. And then as you go out with this coronal mass ejection that's being launched, you get much lower frequency emission. That's when you get type 2s, type 3s, even type 4 bursts as the structure moves out and the shock front moves out with it. So as you go down, or as you go higher and higher and higher in the solar atmosphere, the solar radio burst that's associated with these different things happening gets lower and lower in frequency. And that has to do with the electron density. So the solar atmosphere is very, very dense down low, but it becomes more tenuous, just like the Earth's atmosphere does. It becomes more tenuous as you go higher in atmosphere. Well, the more tenuous it is, the less chance, the lower frequency of radio noise can be created. So even as this big CME, this big solar storm is launched, as it begins to travel outward toward Earth, believe it or not, that radio emission still occurs, but it gets lower and lower and lower until it actually hits Earth. And you can actually hear some low frequency radio noise coming from these structures, even all the way to Earth. And even once they get inside, there's a lot of kilometric radiation that occurs. So, and all of this I talked about last time. So, this is making perfect sense to hams, yeah. I'm just checking to see if you guys have, is anybody, yes, the sun is a big lava lamp. Is anybody confused by all of that? If you are, please be sure to go back and check the first 2 courses, because the first course I talked about was all about solar radio bursts. The second one tied in the solar radio bursts with the coronal mass ejections that were coming, traveling to Earth, and also the dynamics of the solar flare. Because then we started getting into, okay, you've got a radio burst that occurs, but what is the flare that drives it, and how is it associated with the flare, the X-ray flux that we see, or what is the gradual phase versus the impulsive phase versus the, all sorts of parts of it. And I think I even talk a little bit about that. But the details of, let's say, this side. The details of the radio bursts here in this chart is included in, I believe, I believe both courses, but the first course especially. This goes into the types of radio bursts that we have that are beyond microwave, that are beyond the hard X-ray emissions that occur right there basically at the source regions of the sun. These are the types of radio bursts that actually will travel out into the interplanetary medium. I shouldn't have said it that way. That's wrong. These are the sources that are associated with the coronal mass ejection that is traveling out into the interplanetary medium. At least type 2 and type 3 are, and even type 4, that pretty much driven by the shock. And here's how we put the whole picture together. I saw something about the weakness of the Earth's magnetic shield. Yeah, I might do a course on that eventually. So so here is the model that you're kind of hopefully getting used to by now. It's becoming old hat. There's the low loops, there's the solar wind stuff, and the arrow is showing that big CME kind of launching out. It's not really showing the actual CME itself, but it's showing the trajectory of particles and stuff that's coming out. And you can see the frequency of the waves, of the radio burst from 1 to 10 gigahertz down there at the foot points, and then 500 megahertz right about where the microwave emission occurs, and then 300 and going down, and then even way out here in the solar wind, you're seeing like 20 to 30 kilohertz. So we're into kilometric radiation, and that's pretty much the way it works. Again, you've seen this plot before. This is the frequency versus time. So you have a time of the flare that's at 0. It goes out, in this case, only out to 90 minutes or so, so it's not very far away from the sun yet, but it will, like I said, this stuff extends all the way out. And you see frequency from basically 10 megahertz all the way up to 3,000 megahertz. And you see all the different types of radio noise. You see type 2s, type 3s. You have the type 4, which is that big cloud, which is really what continues out through Earth. Even as that CME travels towards Earth, you get this type 4 noise that just continues, as well as the type 2 storm noise, and on and on. So this is the kind of radio noise that we see all the way out to Earth, and it can be very complicated, as you can see from this plot. This one actually even shows you, and again, I've gone over this before, and this is in the last course. You can see from this is over now a period of days, and again, we've got frequency going up on this side. And you can see the type 3 burst, the type 2 radio emission, and then as this thing continues to travel out towards Earth, bam, right there about 9 o'clock, says the CME shock hits at wind. So this is the wind spacecraft. This is sitting up. This is our upstream monitor, at least at the time. It was like ACE. It was located at the same place ACE was at the time. And you get this burst, this radio burst here, just simply from the noise of the radio noise from the shock hitting the actual spacecraft, the instruments anyway. And as it passes through and actually goes inside the Earth's magnetic shield, there's all this other radiation noise. So, you know, it's not quiet by any stretch. Now, luckily, most of this noise here is not at frequencies that bother satellites. I mean, the ones that bother satellites are the ones way over here that are at the high frequencies, right? I mean, you know, you talk about the L1, L2 band for GPS, for example, at 1.4, 1.5 gigahertz. You're sitting here. And so that's why we get problems right when the solar flare occurs. It's still the radio burst, but it's the stuff really close to the surface of the sun that actually has enough electron density. The solar atmosphere is still dense enough to be able to create really high frequency radio noise. Whereas the stuff as it travels out, it's the electron density, you know, it's too much of a vacuum. So it just really can't create the high frequency, high energy radio noise that we would get closer to the sun. Okay, and now this is just a real repeat, just to kind of get your mind set on really where radio frequencies are, what matters. I'll stand over here for just a second. And the reason why I'm doing this is just so that kind of remind you what types of things our system, what kind of technologies we have that are really susceptible to this kind of stuff, okay? We have the very low frequency all the way up to extremely high frequencies. You can see the frequency ranges here, and if you prefer wavelengths, you can see the wavelengths. And then if I flip over to this side, so you can see it, there's emergency radio that fits in this region, and actually if I go over here, I've actually spelled it out. So you can see extremely low frequencies, you can see that's maritime mobile. You can see low frequencies, we start getting into, and middle frequencies, we start getting into radio, AM radio, and then we get into FM radio and television. And airline communications, as we get even higher, we get into wireless devices and cell phone technologies and sat phone, you know, so satellite phone technologies. And then we get up into the very high frequencies, the extremely high frequencies, we're getting into satellite communications. But really, everything from, geez, I mean, everything is affected. It just depends upon to what degree it's affected, right? Obviously, when you get into the really high frequencies, unless you're sitting up in the ionosphere, you know, up in the upper atmosphere, and you're making communications, long transmissions, you're not going to be affected all that much by a solar radio burst. So your wireless devices inside your house, that's not a big deal. As we do 4G for our cell phones, that's not going to be a big deal. But 5G, that could be. It's questionable whether or not we're going to have issues with radio bursts on your cell phone transmissions as we begin to adopt 5G technology, because they're changing the frequency on which cell phones work, you know, the cell phone towers. So that's a real question mark right now. But at any rate, you know, that's going to be a wait and see kind of thing. And you'll see with the examples today how disruptive this stuff can be and what the sun really can do. But this gives you an idea of where we're going. And I think, oh yeah, it even put 5G in there. I missed it. See that? It even has 5G way down here. I didn't even realize that plot had it. But that's exactly right. We're going to be migrating over to this. And the sad thing is that we've become so complacent to think that because our wireless devices and our technologies have worked so well, we keep thinking that we can just apply them in any case and just change frequencies ad hoc, whatever we need for our particular purposes, and we don't have to worry about anything. But they forget that the reason why satellites work well is because they're designed by people who actually have checked to see how to get around space weather effects. Satellites and satellite signals, oftentimes we have mitigations to try to figure out how to run through or operate through a space weather incident. Or we just put things on hold and just say, okay, there's an outage, but we don't explain why. But the people who make the satellites and run the satellites know. But now we have all these people down here who are trying to use some of the same technologies that we've been using up there for a long time, and they have no clue. Why would they care about space weather? It's never affected them, right? Well, yeah, it has. They just don't know that. So we're beginning to see more and more of this stuff crop up. And as these commercial industries come up through the ranks, and Aurora, and space tourism and everything else, we're going to see more and more of this, where these multi-billionaires and angel investors are going to be dumping a ton of money into a technology that is robust sometimes, but really has some major weaknesses. And I think it's going to hit a few people really hard in the face when they realize that, they kind of overlooked something that was pretty critical. So, fiber optic system is better. Yeah, fiber optics are better, not in space. They're not very radiation hard in space. Fiber optics darken and turn brown and crater pretty fast. We know that because we use fiber optics for inertial navigation. And it can be a real problem. But fiber optics in the ground, yeah, it's better, but who wants to lay all that fiber optic cable? Especially when you can get a MEO spacecraft that actually has lower latency than fiber. And that's really what Google and Amazon and all these other places, all these other companies are saying, that they can actually get even faster than fiber internet speeds. Simply, I don't mean speeds, but reaction times, transmission times. Simply because the path length is shorter. They can get a faster signal through. That's great until until the radiation belts take them out, or half a dozen other things. Starlink is going to be another big one, and you'll see a little bit of that. I may talk a little bit about that in this particular course, but I may save it till the next course because that's when I go into the Carrington event, and I mentioned something that Dolores Knipp had in her talk about the 1972 Carrington event, where the atmosphere takes out a lot of LEO satellites because it puffs up, and suddenly all these LEO satellites find themselves in different orbits. So it's a very unique thing about LEO, and unfortunately that's where Starlink is. So it's going to be interesting. Okay, so let's see. Just looking at you guys. What is this? Delivery drones can fall out of the sky. Yes, yeah. As a matter of fact, that's going to be one of the examples that I talk about. So let me get through this. This is once again the review. This is a 2-ribbon flare, the classic thing where we talked about the transition region in the chromosphere. We called the impulsive phase. That there were, you should remember this from last time. Whoops. Let me stand on this side. You have an impulsive phase, you have a gradual phase, and you have different accelerations and stuff like this. And I had this all color-coded, so please go back because this is what begins to link what you're seeing with your eyes when we're watching solar flares evolve and what kind of radio burst is occurring at the same time. So this was one of the things that really started talking about that and kind of tying it all together. And in this case, I'm actually going to show this. I think this video continues to move over. But what we had and what we have on this one is radio noise here, and then an H-alpha, more optical stuff from Big Bear Solar Observatory. And you can see how the two, during a solar flare, how the two evolve differently. You can see the radio noise contours on this side here, and they peak, they turn red really early on in the flare. Boom, right there, there's the really red stuff. And then but you see this 2-ribbon. You can see the 2 ribbons, basically 2 ribbons. They're a little bit ugly, but you can see one bright region and another bright region kind of light up, kind of like in a little stripe. See the 2 stripes right there? That is more what we see in the extreme ultraviolet and the X-ray emission, and it's obviously very different from the radio noise. And as we look down here, we've got a plot that actually shows the soft X-ray, which is not the H-alpha, but it's close enough. You can see the soft X-ray in this case and the radio noise. The soft X-ray peaks much later, and as you can see, it's very similar to the H-alpha stuff here. You can see the ribbons just light up and stay lit for a long time, whereas the radio burst happens very, very fast. That's the yellow trace down here, and it happens very fast and dies off. So depending upon the frequency of light that you're looking at, you're going to get a different picture, but we can link the two and know where the sources are occurring and what phase of the flare is kind of like responsible for what kind of, or is connected, is associated with what type of radio burst you're going to get. And in this case, do I have to play this? Yeah, I do. Okay. And in this case, we're talking about the emission, how the emission varies with the phase of the flare. If I can pull this back again, this video was also in, gosh, I can't get out of the view. This video was also in the, you know what, I'll stand on this side. In the prior course, if I get far enough over this side here, I'll stand in front of the magnetic configuration because it's not really relevant for this particular topic. But you can see the 3 different traces here. They each are showing a different wavelength, therefore a slightly different height in the solar atmosphere, but they're all EUV. So this is all extreme ultraviolet emission. But you can see in the Eve data, this side here, yes, the 9.4, that's angstroms, that I believe is this plot here. The 94 angstroms, 9.4 nanometers is 94 angstroms. So that's this plot here. And this thing is, you can see it's basically the bright part of the flare. And when it plays, is it going to play again? It stopped. Let's play again. When it plays, you can see on that particular wavelength, you can see it brighten really, really fast and then kind of die down. But if you look at the yellow picture, see the bright part in the green, and then it dies down reasonably quickly. But if you look at the yellow picture, which is right in front of me here, look at those loops above, higher level in the solar atmosphere. They actually brighten later. Okay, so the flare is basically already done. The hard emission is already done. And now, if I scoot back even more, you can actually see those bright loops begin to brighten. Here we go. Ready? You're actually seeing it brighten in the blue first. And now, look at the yellow. See the yellow brightening? Those are what we call post-eruptive arcades. So depending upon where you're looking, what frequency of light you're looking at, you can actually watch that flare and watch the different phases evolve. And I'd go into that far more intensely in the prior course. But I left off, I believe, with this plot, talking about how flares can cause atmospheric changes. So even just from solar flares, not even a radio burst, but just the solar flare, the light emission from the solar flare and all the different wavelengths it gives, can actually cause, if I can get out of the picture here, can actually cause sudden increases. So what we are looking at here is called a sudden ionospheric disturbance, and it can actually lead to GPS disruptions. And as you can see in this particular plot, we've got it kind of reasonably quiet, and then suddenly you get this flare, and look at this big disruption you get afterwards. So you have the X-ray flux on top. You can actually see the big peak of the X-ray flux in that black line peaks prior to the ionospheric disturbance, but then all of that burning afterwards in the post-eruptive loops and everything else ends up continuing this ionospheric disturbance. So these things can cause radio blackouts as well as GPS disturbances. And so when we have these big flares, especially the long duration ones, it ends up wreaking all sorts of havoc in the ionosphere. So now what I'm going to talk about, let me pause for just a second. She's getting good at this. Oh, thank you. I was nervous that I was going through it too fast. But again, if anyone gets lost in this particular part, please go back to my prior courses, because all of this was just simply review, just to kind of get your mind back to where we've been. Will the new... Uh-oh, I heard something. It looks like my audio's okay. Let me check. Is my audio still good? Yep. I heard a weird pop, so I thought maybe that might have been my audio. Somebody asked, let's see, will the new 5G kill birds or insects? Well, you know, the cell phone towers right now, they try to get the birds and things not to nest in there because, yeah, just the microwave, just any type of emission with really strong RF transmitting capability is going to, you know, cook any wildlife that might actually light and land on these structures. So I'm not sure how much research has been done on that. But anything where you've got a lot of really strong electromagnetic radiation, it's not good for biological creatures because we are electromagnetic in our own right. And these things set up currents and potentials in our own bodies that can really throw off our own electrochemistry. So, you know, and again, the medical research is just beginning to catch up to, or just wake up. I shouldn't say catch up, wake up to the fact that this stuff is pretty serious. So we shall see. We'll see how fast or how easily 5G is implemented, because there's a lot of other obstacles to implementing 5G. And the space weather component is just one of many factors. So what are the flares to come, and what extent will they affect the Earth? Well, you're about to see some of this. So you make it easy for a high school dropout to understand. Thank you. You're very welcome, and don't call yourself a high school dropout just because you didn't finish high school. You know, some of my best friends are that. They ended up getting a GED later in life, or they didn't bother. Some of the most brilliant people I know never finished high school. So I do not judge people based on their credentials. That has always to me been a fallacy. And I will continue to look at people and just take them, you know, one-on-one. So don't talk about yourself that way. But it makes me feel good that I can teach non-experts. You can call yourself a non-expert if you want. I can teach non-experts the crux of what's going on with essentially their weather. It makes me feel good knowing that I can do that, and you guys all help me. So, you know, it's a two-way street. So keep asking the good questions, and if you don't understand, my Lord, just tell me, and I'll figure out another way to explain it. And once I get the right, the right way, then I'll remember it, so I can use it for future non-experts. So appreciate that. Okay. How do these emissions, hi Francina, how do these emissions affect the different layers in our atmosphere? Yeah, you know, a lot of that isn't understood very well yet. I will talk a little bit more about that probably in the next course when I talk about the Carrington event, because that's when I'm going to go into a little bit of the work that was done in the 1972 event, reconstructing some of the thermospheric effects, which means basically our upper atmosphere as it goes from being neutral to you know, further out in the even higher higher in our upper atmosphere out through the ionosphere. And there are some dramatic effects that occur. So I will talk a little bit about that, but probably not in this talk. But I will be. You'll see enough in terms of by proxy. We won't be going into exactly what the atmospheric effects are, but you will see when I talk about the GPS, which is coming up here next. As a matter of fact, I'll put it on here. When I talk about the GPS work that Keith presented back in the Space Weather Workshop back in 2010, you will see by proxy how the atmosphere was affected, because you'll see how dramatic the GPS disruptions were, and they're pretty dramatic. So I tried college, but they wanted me to use my book for teaching me. Well, yeah, unfortunately college does make you read, so school, university are overrated. They can be, yes, they can be. I mean, it really is what you take from school as to whether or not it's for you. Thank you for being honest about big money and the future of 5G. You know, they have so many hurdles. I really don't know if they've really thought it through, and we'll just see. I almost hope that they do, because it's going to be. It'll make the space weather effects that much more obvious, and maybe it'll accelerate some of the attention given to space weather. Can a certain type of a solar storm wipe out our ozone? Yes, yes, it did back in, let's see, the 1972. I have data on that, and that will be the next class. There is, and as a matter of fact, I might have even gone over it. I know I went over it for Patreon people a while back. I have a video on some of the stuff I will be talking about in the next class, and I did that, geez, a while ago. But yeah, it knocked out our ozone. It made a huge hole in our ozone. It was a solar radiation storm that actually did it, and it happened during the Carrington event, or during one of the Carrington events. And the models show that it took about 4 years for the ozone to come back. So yes, space weather can remove ozone from our atmosphere and just cause some major issues there too. You know, these are things that people don't understand that space weather does. So, okay, yes, too much ridiculous conspiracy out there. Right, I'm trying to separate some of that from the reality, so that's why I go over this stuff in real detail with real data instead of just saying, you know, pointing at images of SDO and say, look at all the alien spacecraft that are feeding off our sun. I will actually show real data that have been done, that have been worked on by scientists in trying to elucidate real problems that they can solve. So this is impacts of the December 2006 solar radio bursts on the performance of GPS. Any of you who know about these sunspots, as I've talked about in the past, what happens when you have a sunspot that is going to give us huge events? It's usually what we call a bad, I call it a bad actor. I know a couple other people, a couple other scientists I know, they call them bad actors. They rotate into view or they emerge on the sun. And remember, the sun takes about 2 weeks to kind of rotate something from the east limb all the way off to the west limb to go to the backside. And if a sunspot is a bad actor, it remains a bad actor. If it's really bad, I mean, it just fires off storm after storm after flare, radiation storm, solar storm, boom, 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 and it's just rapid fire. It's like being, you know, beaten up by a pro boxer. You don't just get one kind of space weather event. You get a whole slew of stuff thrown at you constantly for a week to 2 weeks. And that's really what you end up seeing in these examples that I show, both today and in the next course that we give. So that's why it says impacts of the radio bursts, plural, because you will see there's a series of them. And special thanks to Keith, if I stand out of the way, to Keith, who gave the talk, Charles Serrano and Christopher Bridgewood. These guys did a great deal of work here. And granted, it's almost a decade old, this information, but it still isn't out in the public eye, sadly, because people just don't get it when it comes to space weather. Okay, so what we're talking about is some extreme solar activity from active region 10930 back in 2006. That was the full designation of it. And you're looking at the, I believe, the X-ray flux. If I can get out of the way, back in the day, from basically December 4th all the way to like the 19th, or yeah, 18th or something. And you can see what's circled are the four big eruptions that occurred, or you know, solar flares that occurred. Right? You got one on the 5th, you got one on the 6th, you've got one on the 13th that I'm blocking, and one on the 14th. Okay, so again, this is from a single active region, and it was a bad actor that just went bam, 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 and just spit stuff off the entire time it was rotating across the solar disk. Now, I'm not going to bother showing the details of that solar flare, just because that's just more detail I would have to take time to go show, and I really just want to talk about the effects in this particular talk. So, out of this group, the one on the 5th, which is like the first one, was the most intense when it came to the X-ray flux, but as we've learned from the past couple courses, just because something is really intense in X-ray flux doesn't mean it's going to be super intense in radio flux as well, or a radio flux of a particular frequency. And as we found out, it was actually the radio burst on the 6th, from the flare on the December 6th, wasn't as intense of a solar flare. As you can see, I think does it say the peak? Oh no, it's giving a time. Oh yeah, down here, I forgot. I'm blocking it, of course, that's why. December 5th, you can see December 5th, so we're talking about the four flares down here. And when we say L-band peak flux, this is the solar flux, or not the solar flux, but the flux of the radio burst in the frequency range where the GPS L bands are, which is you have L1 and L2. There's two bands. And I don't know if I put on their frequency here, but they're 1.4 and 1.5 gigahertz, I think. Or it's 1.5 and 1.2. L1, I think, is 1.5. I have it written down here in one of these slides. And then L2 is, I think, 1.27 something. So it's right in the, just above 1 gigahertz in frequency range. And it was actually the December 6th flare that gave, what is this, over 1 million solar flux units in that range for the radio burst. So huge. So as you can see, the December 13th flare then gave, you know, a decent amount, and the 14th was, okay. But it really was the December 6th flare that did that, and that's this one that, by the look of the X-ray flux, it's an X flare, you know, okay, whatever. So this is a perfect example of looks can be deceiving. So all of you who look at the X-ray flux who are radio operators, and you're looking at the X-ray flux to gauge how big your radio burst is going to be, this is a perfect example of saying, okay, there's a flare right now, but that doesn't necessarily correlate with how intense the radio burst is going to be, because different frequencies of light will look different for different flares. And I think, okay, so let me see what else is on this chart. I said, basically that December 6th flare was the one that caused a huge amount of GPS tracking and positioning errors for basically the entire sunlit side of the hemisphere. You want to know how bad? How about this for bad? See all the, so this is the this is the Western Hemisphere, as you can see, and you can see all of the position, you know, the GPS receivers, essentially. The IGS cores tracking, and the WAS receivers, these are high precision GPS receivers, and they're recording data at about 30-second cadence, but the red ones, I'm trying to remember what the red ones are the ones that ended up being affected. The red ones are the ones that were able to track less than 4 satellites during this solar flare burst. And if you can't get 4 satellites because the sun is screaming so loudly, you can't get a position solution at all. You need at least 4. That's a minimum. And remember, we have a constellation of GPS satellites that are all over the sky. But if the sun is screaming that loudly on the sunlit side, you have to be able to at least get 4. And look at all the red dots all over the United States. I mean, and above and below. Horrible. Excuse me. So, if I go to this side, this is where we get into precision approaches for aircraft. Okay, so you can imagine with the sunlit side of the Earth being hit that hard that GPS receivers can't even, these are precision GPS receivers, can't get a lock basically on these satellites to be able to get a position solution because they can't hear. It's not that the satellites aren't working. The satellites are working fine. It's just that the sun is screaming so loudly the receivers can't hear the satellites. It's that proverbial cricket in the train tracks. You guys remember, but I bring this up every now and again. You can hear it. Let's say we have a cricket and we have it, the cricket is near a set of train tracks, okay? And the cricket is chirping, and if you're standing nearby, you can hear the cricket just fine, right? And the cricket continues to chirp. And then a train goes by. And as the train goes by, can you hear the cricket anymore? Is it chirping? It could be chirping, probably is chirping. But can you hear it anymore? No, because it's being drowned out by this hugely loud train that's screaming down the tracks. Once the train goes by and it's gone, now you can hear the cricket again. So the satellites are the cricket and the sun is the train. And our solar radio burst is a train. So while it's screaming, the satellites will be chirping just fine. But the receivers on the ground have no hope of hearing them. And that's why they couldn't get locks, right? But what does this do when you're trying to do a precision landing in an airport? Okay, how do you deal with it? Well, basically things just don't work. Here's an example. This is a brief loss of the vertical guided approach for high precision GPS, because you know all commercial aircraft now are basically guided. When they do their landing, the pilots flip a switch, or probably flip a bunch of switches, and then sit back and let the computer land the plane for them with this very high precision GPS stuff called WAS, the wide augmentation array, some system, I think. And in this case, you can see that pink area, all that pink. Hopefully you can see that. Yeah, you can see it there. Okay. The guidance system failed. They couldn't get, because of all of this noise, because of all of the stuff that was affecting, you know, all the screaming that was going on from the sun, they completely lost the capability of landing planes. So could you imagine being a pilot trying to land this plane, and suddenly you get all these failures in your system and you have to quickly manually try to land this plane? Well, that's what happened. And as a matter of fact, there's an example of, not just in 2006, but there's an example just, I think, in 2015 with Sweden, where do you guys remember back then? It was like November of 2015 or something. Might have been November of 2016. The Copenhagen, the airport, they had to shut down for about 2.5 hours. Now, there was a big solar storm going on at the time, but there was also a big solar radio burst that happened at the same time. Because again, it's a bad actor. So we had a bad actor on the sun, and it was firing off solar storms, and it was firing off solar flares all at the same time. So we had gotten hit by a solar storm, and the solar storm was in full force, and then the bad actor fired off a big solar flare with a big radio burst in it that affected the WAS system just like this. Copenhagen had to shut down for 2.5 to 3 hours. All the flights had to be rerouted. It affected basically the entirety of Europe and all the airline flights in that arena. So if any of you lived in that area and remember that, that was a big deal. And it took them a while to figure out what was happening. They didn't realize until later. The Mosswalk came back and said, yes, this was because there was one of the solar flares that occurred had a huge radio burst. And it was right in had a lot of energy right in the frequency range of GPS. Now the interesting thing is, the frequency range of GPS is the same frequency range of satellite phones. So if you see GPS go down, most likely you have issues with satellite phones. So for this particular situation, I bet you they didn't have satellite phones working either. But of course, people didn't, this data isn't talking about that. But if they looked for the satellite phone usage and tried to do a forensic study on it, they'd find exactly the same thing, that all the satellite phones went out. Do you think amateur radio operation and emergency operation or radio operation would be useful at this time? Not at all. This is probably such wideband noise it'd kill everything. So this is part of the issue. This is hopefully I got that I've made that clear to you guys. Let's see. And Carrington stronger? Oh, is the Carrington stronger than this? Again. And I'll talk about this more in the next course, but here's the trick with the Carrington event. Most time the Carrington events, when we talk about the effects of the Carrington events, we are talking more about the geomagnetic storms that occur. We're not talking about the solar flare and the radio bursts. The solar flares are oftentimes white light flares. They're very, very intense, meaning that they have a bunch of light. They have so much emission that they give off emission not just in X-rays and everything else, but they even make it down into the visible range so we can actually see them with our own eyes. That's how we know how intense they are. If they can make it, if you can have white light being emitted from your flare, that means that flare is occurring way out. I mean, way out in the solar atmosphere, because you can actually, remember, as frequency goes down, or as you go out in the atmosphere, the frequency of light goes down. So if you're emitting that kind of light, then this is a really big flare, because it's so far out in the solar atmosphere. But the thing is, in most cases, the effects that we've had, at least for historical, the history of Carrington events, which have been reasonably, early before we had modern technology, we don't have a lot of knowledge and a lot of data on what the solar radio bursts were, at least in a bunch of frequency ranges. We have it in VLF and a few others, and you'll see that in the 1972 event. But for the 1959 event, what we really have a lot of records on is actually the geomagnetic storm that hit, because we didn't even know to look for this stuff, that there'd be something traveling once you saw a flare that then, a day later or less than a day later would be getting hit by a big, CME. We had no idea that there was even solar wind at the time. So we didn't know what to look for. And so there's not a lot of data on those stuff. But we do know what to look for once the storm hits Earth and it causes all sorts of problems, then we know. But for radio bursts, it's a lot more dicey to be able to understand that, oh yeah, the reason why my radio isn't working right now is the sun. A lot of people didn't know that back then. So let me talk a little bit about this. This is the radio. These are the receiver networks, or what they call the SCINDA network that they've used for a lot of this analysis. And I'm kind of blocking a little bit here. Maybe I should stand on this side. You've got all of these receiver networks, and the reason why most of the receivers, as you see in this map, I guess, mid-latitude to equatorial located. They're located close to the equator. The reason for that is because of what we call the equatorial anomaly. There in the upper atmosphere, there's something, and I haven't gone over this very much, but in the upper atmosphere, there are two bands at low latitudes that follow the magnetic equator, both in the north and the south, all the way across the Earth. And these two bands are filled with an unusual amount of ionization, meaning they're like almost like current systems. But they are, I'm trying to not use a lot of jargon to talk about it. What they cause is a lot of scintillation. And basically that means that they cause the effect of twinkle, twinkle, little star, right? When you look at lights on the city, or you look at the night sky and you see the stars twinkling, that's called scintillation. It's visible because you're looking at visible light scintillating. It makes those city lights look very pretty, and it makes the stars look very nice, and you can sing the song Twinkle, Twinkle, Little Star, and it's all wonderful. But believe it or not, scintillation isn't limited to just visible light, any kind of light, including radio waves. So this scintillation, these bands cause scintillation for radio waves, and it can cause scintillation for GPS as well as amateur radio. And a lot of people don't know this, but in my forecast, for example, when I talk about GPS users at low latitudes, when I say, you know, some of these solar storms, if they're weak, they can help you because they help stabilize the upper atmosphere in your region. This is what I'm talking about. I'm talking about the equatorial anomaly and stabilizing these bands that form. But in this case, the reason why all these receivers are in this region is because they're trying to study specifically. They want to get an idea of how bad the scintillation is during this, you know, in these regions. So that's why you don't see a lot of this for the SCINDA network. You don't see a lot of stations at higher latitudes. But at any rate, the reason why I'm putting this plot up is because I've got 4 different receiver stations that we're going to look at, and this was during that December 6th flare that caused all the problems. And you can see this purple line that goes, you know, kind of up and over and back down. That is the day-night terminator, and I've got it labeled down here. You can see midnight. I'm kind of standing in front of midnight, dawn, noon, dusk. So you can see when they called it the subsolar point over here. That subsolar point that you see right there. Oops, I'm too far over. That is basically where noon was at the time. So everything inside this region is daylight, and everything outside is actually nighttime. And so they looked at 4 different networks, or 4 different receivers, 1 right at the day-night terminator, as well as 3 on the daylit side. And we're going to go into that. Now, the ones that are in yellow are actually dual frequency, which means they're high precision GPS because they can actually use both the L1 and the L2 signals to then, what they do is, because the L1 and the L2 will be going through the same parcel of, same part of the upper atmosphere, they'll react differently to problems, space weather problems, conductivity errors, bending, refraction, scintillation. They'll react slightly differently because they're slightly different frequencies. And because we understand the physics of how all that, how they react, we understand why they would react differently. By comparing the two, we're able to subtract out what some of the problems could be. This is how dual frequency GPS systems actually are higher precision than single frequency. If you only have single frequency and you're just using L1, for example, like all of our cell phones are, and commercial drones typically, right? All the hobbyist drones, single frequency GPS. There's no way to subtract out the differences. There's no way to characterize what might be going on in the upper atmosphere because you only have 1 frequency. You don't know, you don't have a ground truth, you don't have any type of basis for comparison. So it causes you to not really know where your errors are. But all these yellow stations actually had dual frequency. So they were actually able to try to, try to correct for these issues. And if you notice, all of the stations that we're looking at are dual frequency. So this is high precision, the ones that can do better in space weather events than the single frequency stuff. So what we're going to be looking at is how these particular systems went out and they're even more robust than your cell phone. So, food for thought. Okay, so getting you acquainted with the actual flare itself. This is the Owens Valley solar array, and the RHCP is right-hand circularly polarized. Don't worry about what that means. It just means how the radio burst, how the wave looked. There's polarization in these electromagnetic waves, and it matters for science, but it doesn't matter really for our discussion. But that's what it's labeled. At any rate, between essentially 18 to 2000 hours on December 6th, you can see with the frequency. Whoops, I'm standing right on it. Let me go over here. Sorry, I'm looking at the other thing. You can see the frequency goes up on the left here, up to, and these are gigahertz. So from 1 gigahertz up to 5 gigahertz, and you can see the time 18 to 2000 hours. Let me stand back. And if I stand back even more, you see L1 and L2. That L1 and L2, those are, and you can barely see the black line that kind of cuts through. Do you see the black horizontal line that cuts through where those L1 and L2 are? Those are the frequency bands of GPS. And if you notice, there's a big yellow part right here. Yeah, right in this area. That intensifies right where the L1 band is. And that was one of the killers. It also, and it intensified down at L2 as well. But that was the real killer. And if you look at I think this is the X-ray flux. Oh no, that's the power. So you can see in the the intensity of these flares, or the intensity of the radio bursts at the Owens Valley solar array. And you can see that there were 2 peaks, but the one in the frequency range that really nailed it was the one that you see with the radio, with the contour with the yellow, right at the L1 frequency. Okay, and if I flip over here, you can see, yes, the L1 band, I knew I had it. The L1 band is at basically 1.575 gigahertz, and the L2 band is 1.227 gigahertz. Or if you prefer megahertz, it's 1575 and 1227. So that's where the L1 and L2 band. A lot of satellites have their satellite phones at 1.45 gigahertz. Some of them have them at 1.5. There are some satellite broadcast, for television. Those are oftentimes at like 1.6 gigahertz. So you can see solar, like their DirecTV, for example, and Sirius Radio. I mean, a lot of things operate between 1 point something and 2 gigahertz. This is a very, very common radio frequency to use for satellite transmissions. So I think I probably don't need to. Yeah. Oh, the one thing I wanted to mention is that yes, during this time when this flare that I'm standing in front of happened, the entire Western Hemisphere, that was when it was sunlit. So you think back on that map that we showed just a moment ago, that entire region, this period right here is when the flare happened and when that burst occurred that just trashed the L1 band. Whoops. What happened? I have no idea why my computer did that. Okay. So now let's move on to this. So this is actual data, and don't get too hung up on understanding the time series here. What I am showing, if I can get out of the plot. Can I get out of the plot? Are L1 and L2, okay, and they call it change in carrier to noise density. This is basically a signal to noise ratio. Okay, you're going to see this a few times. The nomenclature is C over NO, or a delta C over NO, the triangle C over NO. That's what the plots are titled. Remember, I'm taking these charts from a scientific talk, so you're going to see a little bit of nomenclature in here. But really, basically what it means is a signal to noise ratio, and how cleanly can the signal come in from, compared to the noise. So the C, if you can almost think about it, it can be, the C is the signal, meaning the cricket, and the NO is the noise. You can get the cricket really being drowned out by the noise. And if you look at these plots, you see PRN to for 27, 28. The PRN numbers, these are different satellites. GPS satellites have a designation, basically their name, and it's always a PRN number. There are PRN numbers, there are PRN codes. So each one of these traces is showing a different signal reaching the ground, in this case reaching ANCON, which was one of the circled receivers in South America that I showed before, a dual frequency receiver. That's why we're using L1 and L2, okay, because L1's on the left, L2 is on the right. And what we're looking at is basically the signal degradation, okay? And I'm trying to see if I can remember, what is it, in dB, yeah, dB hertz, so decibel hertz. This is how much the signal strength, the noise, or the signal quality, signal to noise ratio, how much it dropped. And you can see there were multiple disturbances. And I'm trying to get out of the way so you can actually see the Owens Valley trace below. Okay, and it's not exactly to the right time, but it's close. You can see that first signal pop over here, where the signal degrades quite a bit, and then you get a little hash, and then it really drops when you get to where that L1 and L2, see the yellow in the Owens Valley? That's what I had showed before, right here. Remember from that other plot I showed? Right there. Yeah, that is where you get this, where I've got the red arrow pointing. If I can get my hand out of the way. There you go. Where that red arrow is pointing, that's where you got the biggest, what we call signal fade, meaning the GPS just lost lock. You couldn't get any communication going whatsoever. And the deepest fade for L1, which is this signal here, was 25 decibels, which is quite a bit. It's enough. It's enough to cause you basically to lose lock. It's definitely enough to mean that you just don't have a GPS signal at all. You can't do it. If you're an amateur radio operator, you know how big a 25 dB fade is. Now, if we go to the L2, you see very similar behavior. We don't repeat the Owens Valley plot, but you can see the same behavior, same PRN numbers. So now this is L2 frequency, so slightly lower frequency. This is the 1.27 gigahertz as opposed to the 1.5 something gigahertz. But you still see the same kind of behavior, right? And if anything, in L2, it's even worse. Look at how bad the L2 tracking loss is, or L2 signal loss is, and for how long. Look at this. I mean, is this insane? Look how horrible it is for L2. So it's even worse for L2 than it is for L1. The L2 fade is 30 dB, and the fade for the L1 signal lasted 4 minutes, just for it to fade. The peak of the fade was a 4-minute long fade. For L2, it was over 9 minutes. How many planes land in 9 minutes? Because you can't use WAS. If either of these signals is gone, you can't use your precision GPS. So you can't land a plane. So it's really, in this case, L2 that's driving it. So you get a deeper fade for a longer period of time. And this is all over the sunlit hemisphere. This isn't just one location, one airport, one this, one that. It's everywhere. I don't know about you, that's pretty intense to me. And for those who are interested, yes, solar incidence angle is being taken care of in this analysis. Normalizing the gains has been taken care of. You'll see that. I'll show in just a second another plot that talks about that, where they kind of, I took out the math plot because they actually go into how they did the normalization. But they've tried to take all of these satellites that are in different locations in the sky and normalize them so that the signal strength that you would see would be the same as if you were all looking at them as if they were all right above you. So it's, when people say, well, if you've got the low latitude, the stuff that's laying low on the horizon, then the path length is different, and so the gain will be down, and there's, it's different stuff. They've tried to normalize all that out so that what you're looking at is comparable between each of the satellites. So those of you who actually know your GPS, yes, they did their due diligence. These are quality scientists who've done this work. Okay, so pseudo-range and phase, I'm only going to show this for just a moment, because only people who are really interested in pseudo-phase and range are going to be people who really work with GPS. And I'm not going to explain all of the issues related to it. But I just wanted to show that in this case, this is the pseudo-range on this side. When you get big pseudo-range errors, you lose tracking, you know, and you lose the tracking here, and this isn't anything to do with ionospheric delay. This isn't anything to do with the timing. This is just flat out GPS disruption because of the solar radio bursts. And on this side, whoops, I guess I can still stay on this side. And then when we look at the far side and they talk about the carrier phase, you can actually see the enhanced ionization in the GPS signal because of the way the gain works in each of these. And what happens is that the phase begins to alter and change because the ionization is changing, the conductivity of the atmosphere is changing. So the phase is shifting and it's moving. And eventually when the phase shifts so much, boop, you lose lock because you actually get a cycle slip. And so it causes, as you can see in this case, in this PRN down here, you can actually see it go bloop off the scale. And I've seen that with GPS before during solar flares. And sometimes it's because of old, you know, of some of the older blocks. There are different GPS blocks. You know, we keep putting new versions up, and each version of GPS satellites replace some of what they call the older block. And they are a little bit more robust. They're a little bit better instruments. They're a little bit better, you know, precision. And so the older blocks have a tendency to do this more often with the cycle slips than the newer blocks. So the newer blocks may not be quite as susceptible to this stuff, but they're still pretty susceptible. But you know, people have really looked into how bad it can get. Now on this one, let's see, what did I want to talk about on this particular thing? Again, this is just an indicator. Oh, this is an indicator to show you how much the tracking dropped, especially when you look at things like the dilution of precision and the number of satellites. So up here at the top, let me see if I can, let me flip on this side again. You can see here, this is for the number of satellites that are tracked, and you can see they're tracking quite a few satellites, something like 10, and then it goes, when that flare hits, it goes down to basically 0. You can see you just lose a ton of satellites, and that's when that flare occurred, basically drowned out all of GPS on the sunlit side. So basically it didn't matter where you looked in the sky. If you saw the sun, you couldn't hear a satellite, basically. You could not get a lock on any of the satellites that were chirping their GPS information because the train was screaming, and it's a lot louder than that. And I don't know of another example where the entire sky was like that. There are a lot of times where during a lot of these geomagnetic storms that we have, and we get field reporters, GPS field reporters, typically precision agriculture guys, they'll say that they lose a lot of the satellites that are, you know, directly ahead, above, and then the ones that are lower latitude, that are away from the sun, let's say, they can actually pick up, or it's just something to do with scintillation if they're near aurora, they can get it where the part of the sky that there's no aurora, but they can't get it where you know, they can't get the satellite locks where the aurora is, but they can get it on the part of the sky where there isn't any, and so they lose, you know, those sets of satellites. But in this case, it's the whole constellation that's on the sunlit side. They can't get anything. So you see the degraded tracking. You can see how bad the dilution of precision is, for those of you who know what that is. The max was 43.4. And then down here, you can actually get position errors. So you can see the vertical and the horizontal position errors that all this translated to. Believe it or not, what is it, 20 meters? What do I have, 20 meters and 60 meters? I mean, it's insane. 60 meters. Are you kidding? 60 meters, 180 feet or more. So we're talking outrageous errors, and these types of errors. I have gotten people telling me this kind of thing where they're getting really large range errors, but these are outrageous. So people who really rely on GPS and especially precision GPS, would you want to land a plane if you could miss the runway by 180 feet? I don't know about you, but I would be a little nervous. So these types of things are really unacceptable in the space age, right? But very few people understand that this is the reality of things. Okay, so anybody have any questions right now? Oh geez, okay. What about 20 meters? I don't know what you mean. Let me check to see if you guys have any other questions about this bit so far. Oh, you guys are just arguing about stuff, huh? How can this be accurate when the basic model is wrong? Oh, I don't know. Okay. Sounds like there's an argument ensuing. I hope not. Anyway, let me move on. Comparing observations from different locations to account for the solar incidence angle. I mentioned that they're doing that. Again, these are now all 4 stations that were circled, and you can see this. They all, no matter where they looked, and I won't spend much time on this one, but no matter where they looked for the L1 signal or the L2 signal, they got these degradations, and that looked very, very similar. The only time that they didn't was in one of the stations. The signal was blocked, probably because they were, I think because they were in the night side. No, it wasn't because they were in the night side. They were blocked by a ground obstruction. But then they moved it, and again, the signal degradations in each of these PRNs from the different stations, it looked the same. So it didn't matter really where you were. It wouldn't have mattered if you were 100 miles north or 300 miles west, or it was the entire sunlit hemisphere. And it's just sad. It's just sad. And here's for L2. That was for L1. Here's the same for L2. Again, outrageous amounts of degradation for L2 at these different stations. Do you see that? So it didn't matter really where you were. And this is precision GPS. So imagine with a single frequency GPS how much worse you would be. So when we talk about the conclusions, some of the things they asked were, why were these events unusual, and will they reoccur? Well, it was basically because they were due to intense radio bursts at a particular frequency, and they know that it was the electron cyclotron maser frequency that caused it, because that's where you get the radio burst that is in that frequency range. So this is a burst that's occurring very close to the sun, right? It's not from the CME coming out. It's actually coming much higher, or coming much closer, and then probably in the loops that are forming. That once the CME lets go, the loops that are reforming and all the particles that are shooting down back to the solar surface. That's where this radio burst occurred. And it was unusual because it doesn't happen all that often. Something that has a solar flux, intensity of that magnitude isn't something that occurs very often. There are rules that scientists have used and have gotten over time with their statistics that talk about how frequent these types of radio bursts should be at solar maximum, and how frequent they should be at solar minimum. Because this was a radio burst that occurred during solar minimum or near to, they figure that that this shouldn't happen but once every 100 years. And they talk about that in here. But the problem is, in history, and this is one of the things I've learned as I go back and I look at some of these the historical record and some of these major events that are occurring, the historical record is oftentimes, I don't want to say it omits some of these events, but it loses data. It oftentimes has a very flimsy record of what actually happened. And one of the main reasons for that is because, well, the instrument's saturated. We either didn't have the instrument online, we had the instrument online, it's saturated, or the data was all messed up, so people said, well, this is messed up data, let's just throw it away. And so they don't realize, oh, we needed to keep that. We needed to do some reconstruction and some forensics to be able to discover what might have really happened. So unfortunately, with some of these events that are extreme, the data is just not there. And no, it's not Big Brother hiding things. It's scientists scratching their heads going, I don't know what to do with this, and so they just cast it aside, and say, well, no, we can't include that in the data set because we need pristine data that we can actually use, and that data is unusable. So let's just omit it and cause it be a data gap, because we don't even know how to backtrack that data into anything usable. So really, that's what ends up happening. Is the historical record ends up being where you have these really, really massive events, really interesting events. You go back to the historical record and the data's missing. And it's like, guys, we really needed this. But back then they didn't realize that they did. or they just didn't have a way of measuring it because it was off scale compared to anything they'd ever seen. And that's part of the problem with space weather in general, is that we are very cavalier. Unless you're a scientist, you're oftentimes very cavalier about space weather. And even if you are a scientist, some of these big events you don't realize, man, you know, we just didn't build this instrument that was strong enough to handle it. So especially in the early days, we have a lot of that with instruments saturating. As a matter of fact, in the 2003 solar flare, that's one of the reasons why we lost the SXI, is that we allowed the instrument to be burnt out, basically. The solar flux imager, or soft X-ray imager on the GOES satellite ended up, unfortunately, being left on staring at the sun during the solar flare, and it almost killed the instrument completely. And that happens. That happens with these kinds of events. But what it does mean is that if the largest radio bursts and solar events are missing, let me get off on this side so you can look at this yellow bullet, which is the most important of this whole slide. If the historical events, the largest ones, are missing, probably due to saturation effects or other issues, then that leaves open the question of how often do these large events occur? And are our statistics correct when it comes to that? So we can say, oh, well, these only happen once every 100 years. We don't have to worry about it, which is what science and space policy says right now. But in actuality, if we're not looking at our statistics correctly because we don't have the data, then do we have the statistics correct, and is our policy wrong? And I'm beginning to argue that, yeah, I think it absolutely is. I mean, GPS hasn't been around all that long, and we've already had multiple disruptions, and one that in 2006 that was huge. It was massive. And like I said, there was one in 2015 that took out the Copenhagen airport. And there have been others before and since. So these events occur more often than we really have paid attention to. And this is something that I'm trying to change. So they had a conclusion, and I don't really know if we need to talk about that, other than, just the two highlighted yellow bullets I wanted to say. That SCINDA network, the receivers, they observed nearly identical patterns of the signal to noise fading, and each burst could last up to about an hour. So even though the peak only lasted 4 minutes or 9 minutes, the effect of it lasted an hour. So you had degraded signal, GPS signal reception for an hour with each burst. That's pretty significant. And remember, it's the same thing with when you think of amateur radio, emergency radio, and satellite phones and other things. It's not just simply GPS, but GPS is a very robust data set that we can look to probe what our upper atmosphere is doing and what the sun, how much the sun affects satellite signals, because it's kind of like a laboratory for us to be able to do that with. And then the other thing is, of course, remember, 20 to 60 meters were the range errors, both horizontally and vertically. So that, for landing planes, and this isn't the precision GPS, this isn't even single frequency stuff. You can imagine how big the errors would have been in a single frequency GPS. So imagine your drone package trying to be delivered to your front door, and you're getting range errors of 60 meters or more, right? Probably more, maybe hundreds of meters. Your package could end up in somebody else's backyard. I mean, how do you come back from that? And this is something that I don't think the drone industry understands yet. And unfortunately, we are getting government agencies now that are beginning to enlist drone companies to deliver medical supplies to remote areas that are maybe isolated from being able to be traversed by roads. We're having that happen in Africa. There's a lot of testing going on, which, as you know, as I told you, with the equatorial anomaly, you have all that scintillation, those heavy scintillation bands. That's the worst place to be testing this stuff. So come solar maximum, when these bands are really busy, when these equatorial anomaly is really, intense, along with solar radio bursts, I'm afraid some of these drones in these low latitude regions are going to have some serious anomalies, serious problems. Not to mention in Canada, the Canadian Transit Authority is partnering up with drone companies to deliver packages with these 400-pound helicopter-looking drones. They're huge. And that's Aurora country, another source of big scintillation. So again, very cavalier attitudes towards something that can cause major disruptions. And there's not even a whit of space weather concern. So hopefully, can you describe the layers in the atmosphere in the equatorial region which causes GPS scintillation? Do they have a name or a letter? Yeah, well, the layers themselves, you know, those are all, they're all part of where the electron density increases, or peaks, rather. And so scintillation can happen anywhere in those layers, and typically between the layers. But because of the fact that, and also because we have plasma bubbles and things that are welling up from the neutral atmosphere that then distort the layers and bend them and break them and change them, there's a lot of coupling between the neutral atmosphere and the charged atmosphere above it. And that coupling isn't known very well. And unfortunately, we're only beginning to start studying that stuff in any level of detail, mainly because we have things like GPS. Before GPS satellites became vogue, we didn't have a lot of satellite signals that we could use to sound the ionosphere and do occultations with that we're doing now. And now we're doing a lot of that research with CubeSats, and it's a field that's just beginning to light off. And I think we're going to learn a lot in the next decade. But we don't really know all that much yet. And the beautiful pictures that we have of these, you know, very smooth layers, ionospheric layers, really is not the case at all. And unfortunately, the SCINDA network, I don't know if it's back online, but the SCINDA network was shut down. Because they couldn't, well, there's a lot of reasons, but the SCINDA network was shut down. A lot of ionoson data is shut down. These are the things that people use to probe the ionosphere. The problem is that you need to have, because things are changing so much and so often, you need to have a ton of these ionosons and a ton of these receivers all over the place. And GPS is helping us with that. But it's still historically not something that we've been able to really do. So when it comes to the local structure of the ionosphere and how it affects these signals propagating, whether it's emergency radio or GPS coming down, we just don't have a lot of research on that yet. It's still coming. So hopefully this gives you an idea that yes, GPS can be globally disrupted. I'm about to show you another example. It's not going to go into nearly as much detail, but you'll get an idea. This is with Hurricane Harvey, Irma, and region 2673. Some of you remember this region back in 2017. This was a region that on the sun, if I go over here, you can see this is a magnetogram. It's colored, so it shows polarity of the magnetic field going in and out. So you're actually looking at the sun now and seeing the sunspot polarity. What you don't like to have when it comes to sunspots is the different colors, let's say red and blue, touching each other or coming anywhere close to one another. You do not want magnetic polarities of opposite directions coming close, because that's when you get the reconnection. And as you can see, this region, when it emerged on the sun's disk back in 2017 in September, it grew from something reasonably benign that had essentially one red region and one blue region, to something in 2 days that went red, blue, red, blue, red. And that mix made all of us space weather scientists who were staring at the sun really nervous, because this is a recipe for disaster. This is what you call a bad actor. If you want to know what a bad actor looked like on the sun, there you go. Region 2673 was a very bad actor. And it emerged essentially right when Hurricane Harvey had decimated Houston, right? Here's a guy with a cell phone. He's using a sat phone. If I stand over here, you can actually see the satellite phone he's using. This poor guy hadn't talked to his dad, his family. He had come down. It was the first hurricane he'd ever been in. He had come down from like Arlington or something, trying to find his family. And his battery died. There was no power. There was no way to charge his phone. There was nothing. He had no idea. And he came down to this location where his dad's house was and found his dad's house completely destroyed. And of course, his dad wasn't anywhere around. So he's freaking out. And the CNN reporter just happened upon him and said, "Are you okay?" And the guy on camera told his story. And the reporter gave him his satellite phone to use. And so what you're seeing there is him wiping the tears out of his eyes as he actually got a hold of his dad and found out that his dad had made it out. And they were, anyway, You can look it up on YouTube. It's very touching, and it still gets me. But this poor kid he was like 18 years old. He had never ridden through a hurricane. He had no idea what to expect, and it just, I mean, it absolutely destroyed him. But luckily, at the time, satellite phones were working. This was when Region 2673 was emerging. But in a few days, that phone conversation he was having, that critical phone call, life-saving phone call, wasn't going to happen because the satellite phones would be dead. This is what Houston looked like at the time. Not very good, huh? Yeah. And all of this, and this is what I told terrestrial weather broadcasters. I said, when I gave an invited talk at the National Weather Association back in, I think, was it 2017 or 2018? I said, while all of you were looking down at the hurricane, you know, down at the satellite images, all of us space weather people were looking up at the sun, because we saw this, and we knew bad things were about to happen. So sure enough, in a single week, Region 2673, remember I told you they fire off, it's a bad actor, so it fires off a solar storm and then a radiation storm and then another solar storm, boom, 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 all the way across until it rotates out of view. In a single week, Region 2673 launched, and can you even see that? I'm in the wrong place. How come this disappeared? It says September 3rd through September 10th. I don't know why it got cut off. It launched 4 X-class flares at an R3 to R4 level radio blackout. The scales for radio, for all of these scales, the radio blackouts, the radio blackouts, the geomagnetic storms, and the radiation storms, they all go to 5. That's it. So in a single week, this thing fired 4 X-class flares at an R3 to R4 level blackout. I saw one person actually said that it's been corrected to an R5. We actually got an R5 out of this one. There were over 20, I think there was something like 26 M-class flares all total, at an R1 to R2 level radio blackout. And then there were 2 solar radiation storms being shot at the S2 to S3 level. Remember, the scales only go to 5. And then there were 2 geomagnetic storms, one at a G4 level and one at a G1. And all of this was done in 1 week. And if you look at some of the data that the amateur radio operators and emergency responders were dealing with, here's one of the solar flares that was occurring, okay, along with a radiation storm this is the D layer of the upper atmosphere. You can see the red. Anything that says red is bad. So over the entire sunlit hemisphere, we were having issues, okay, and all in the polar regions because of the radiation storms. As you look at the X-ray flux, here's 1 day of X-ray flux, I believe. And here's the I think an X-class flare right there. And as you can see, you'd have 1 X-class flare, you'd barely get down to the M-class level before another X flare would light off. And this is I think either 12 or 24 hours worth of data. So basically, you couldn't even get down to a non-radio blackout because that's an R1 level is an M-class flare. You get down to the R1 level from an R4, and you jump right back up to an R4 because another flare would light off. So basically the sun was screaming, and once one scream began to die down just enough that you could actually do some work on the radio bands, another flare would light, and the sun would start screaming again. And you just couldn't do anything. On top of that, there were also solar radiation storms, which, once again, I don't know why the plot got covered. I need to fix this plot, but there were solar radiation storms. We had 2 solar radiation storms going. Basically, every time you saw a solar flare, you got a new burst of solar radiation. Now, Nathaniel Frizzell did an amazing job. He put out a paper just this year, and I can put a link to it for those who want a copy. Actually, and I'll sit over here on this side so you can see his plot. This is one of multiple plots from his paper. You're looking at multiple different radio wavelengths in amateur radio. And this is before the flare, this is during the flare or after the flare, or during the flare. And you can see that the color, it's color-coded based on frequency. Hopefully you can see what frequencies there are. The red and the green are the emergency radio response bands. And beforehand, you can see there's a lot of communication. Obviously you can see that also the daylight part of the hemisphere is what's white. What's shaded gray is nighttime. And you can see there's a lot of communications going on in the daylight sector before the flare. And then after the flare hit, Look at the difference in the green and the orange. Look how much communications dropped off. And this is for the, I think, reverse beacon network and as well as the whisper network. So these are reasonably robust. We're talking about, you know, CW communications and ones that have very, very small bandwidth. So these are the most robust of all amateur radio communications that can be done with so they will last. They will last the longest. They're the hardiest through solar flares, and it still decimated them. And this was for the December 6th solar flare. This was the X9.3. This wasn't even the worst of them. The worst of them happened on September 10th. And I definitely say that you need to take a look at Nathaniel's work because he did an amazing job on this paper. He's got so many plots. This one now is showing two separate flares. This is the one, let's see, on September 6th again, and the one that happened like 12 hours later. This is both for Europe. This side is Europe. This next side is for the United States that I'm standing over, and I'll get to that in a second. The reason why we talk Europe is because Europe during those two flares was on the sunlit side. If we look here, you can see, let's look at the second panel up here. You can see when the two flares hit. Okay, so that's the X-ray flux. See the two? Now, what you'd expect as soon as the X-ray flux jumps up, you'd expect all the radio communications to go out. And that's exactly what you see. When I look down at these four panels down here, these are the radio communications, basically intensities over a range. I believe it was a range of, over a frequency band. And they're different frequency bands. And the white dash line that goes across, that's showing, it's the solar zenith angle. So basically when it's at its peak, that's noon. When it goes down, it's getting closer to dusk. When it drops down to basically zero, that's nighttime. So this is why he did Europe. It was because Europe, as you can see, for the most part, was always in the daylight sector during these particular flares. So they will be the ones that will be susceptible. You know, any of the nets in Europe will be the ones that are susceptible to solar radio bursts and screams, right? And as a matter of fact, if you look on this side here, way over here, this is the density for each of the bands. This, if you're curious where the communications were coming from, you can see that this is a map of Europe, and you can see where the communications were coming from, where the contacts were being made. He wanted to kind of show where those contacts were being made. But as time goes on, you can see right when those solar flares hit, all the communications die for a certain period of time. How much those communications die really depends upon the frequency of the band. Unfortunately, the two emergency communication bands get hit pretty hard. You can see, I think this is 7 megahertz? Yeah, 7 megahertz down here. Look at how badly it gets hit with that second flare. It gets hit so hard that it takes a long time for the signals down here, the signals to grow back. See, whoops, I'm too low. See how long it takes? Hours upon hours. So you can see how dramatically those flares just killed radio communication, just went completely silent, and no contacts were made. Now, if I flip over here to the United States, again, on these plots here at the side, you can see where the communications for each band, where the communications are occurring. And in the cases of these two, it's almost all over the United States. Now, the reason why this isn't quite as telling a map is because, for the most part, for 3/4 or at least half of these other panels, these four panels here, the United States was in the night side, so it didn't, it was protected. You can't really, you can't hear the sun screaming if you can't see it. So communications was just fine, but as soon as we started rotating, as dawn breaks and the sun comes into view, look how much the radio communication dies. It's pretty telling. Now, granted, some of that has to do with the frequency of the bands that we're using, but nonetheless, radio communications was definitely pinned down. But it's much more telling with the European side for this particular flare. And again, this is just a smidgen of work that he had done, that Nathaniel had done for this paper. And I really strongly suggest you check it out because it's very, very telling. He even goes into the geomagnetic storm that occurs later. Now, for me, I'll be a little bit with what happened personally with me during this, because I was actually doing a lot of the field reports and things like that. I was on Twitter and I was getting field reports from aurora photographers all over the world, and this is what the aurora looked like in New York, even though we got aurora for this solar storm clear down to Arkansas. So I just like this particular picture. It's very pretty. This was a field reporter in Brazil telling me that basically we had no Brazilian direct TV. So the radio burst was so dramatic that and this was during the solar flare that occurred on September 10th. It was in the gigahertz range and it killed direct TV. So that tells you it's about 1.6 and lower, 1.6 gigahertz and lower is where the sun was screaming. Here's the reverse beacon network during the daylit side. Now the reverse beacon network for the September 10th event, you can see all the stuff in Europe, no problem, because it was on the night side. But the reverse beacon network, again, this is some of the most robust amateur radio and emergency communications that you can do, because it's all CW, it's all Morse code, it takes a very little bandwidth. And so if these signals can't make it, what signals can? And then let me open this. If that doesn't get you, maybe this will. Let's see if I can stand on this side. No, I've got to stand on this side. So let me play this. This was given to me by Andy Smith, who's a radio operator. These are all, during the September 10th event, these are all the radio communications that we're seeing. The different colors are different frequencies, but look what happens. Pause it right there. Actually, I think I can go one more. Yeah. Look at that. Can you tell when the solar radio burst occurred? There's not a single communication being made in the whole entire Western Hemisphere. That little yellow dot that's above South America over here, if I can get all the way over here, I guess. See that thing? Back, back, back. There you go. See it? See that yellow dot? It's in there somewhere, right there. That yellow dot, that's the subsolar region. That's where noon was. So it shows you the sunlit side. It was all noon. You can actually even see the shadow of the terminator back here where Europe, and that's where all the communications is being done, because they don't see the sun anymore. And you know where Irma was at this time? Let me show you where Irma was. Right there. I don't even have words. There was no radio communications going on. The first responders couldn't talk to anybody. They were done. They were done for hours upon hours upon hours. And this continued until after Irma had already decimated Puerto Rico and it was moving into the Florida Keys. And they still couldn't get any radio communications. And then the solar storm hit at night, right? Or hit and the night side went bad. So you couldn't even get any radio communications. You couldn't get it on the day side because of the solar flares. You couldn't get it on the night side because of the solar storm. And the satellite phones. So we had the Red Cross telling me that the satellite phones, as a matter of fact, Francine, I think you were the first one to alert me to this, and I found out later that yes, this indeed was true. The Red Cross couldn't use their satellite phones. They thought the hurricane was interrupting their satellite transmissions, the phone transmissions. They had no idea that it was a solar radio burst and it was geomagnetic storm related and it was space weather related. But that's what was happening. And so, believe it or not, on Russian TV, I actually got picked up, no, over here. I actually got picked up on REN TV. They were talking about the space weather incidents along with the hurricane. And they actually picked up my YouTube video and they translated, you can see my name in Russian. And I actually have a copy of this video. I'm not including it now, but I actually have a copy of this. They put a Russian translator on and translated over what I was saying. And the part of my video that they showed was when I was speaking directly to the amateur radio operators and telling them, look, you're just going to have to tough it out because this is what's happening. And you know, work this side, work the day side until there's a solar flare, but then you can work the night side until the solar storm hits, but then you won't be able to work that. So I was giving them that information, and they actually broadcasted it on one of their state-run networks. So it tells you where we're going with this and how critical it actually is. And let's see, before I get to the conclusion, so this is it. This is the end of this particular set. I will have another set of examples in my next talk. Let's see what you guys have to say. When you actually have any information on what happened with radio waves by the sun, you can see this, by the way, on the station that you're listening to fades away. Yes. Yeah, there are people, it's funny. It's funny. There have been actual works, and I forget who I was talking to about this. This was a radio amateur, I think at the Pacific Northwest convention that I went to recently. I was asked to speak there, and they were telling me about how you could actually, if you worked the bands long enough and you worked it from, let's say daytime into dusk, or you worked it from nighttime or early morning pre-dawn into the daytime, you could actually hear the stations. You could tell when dawn was coming towards you, because you'd get certain stations in certain areas, and then those stations would disappear, but then a new longitude around the Earth would then come into, you could make contacts with that longitude, and then those stations would fade, and then another longitude would come into, audible range. And so you could actually work these stations, and if you had a map or a globe in front of you, you could actually watch how the dawn dust terminator marched across the surface of the Earth, just simply by listening to what stations you hear. And this was during quiet time. And I thought that was really neat, is that you're actually, through amateur radio, you can actually hear the Earth turning. What a neat kind of, way of owning your planet, and owning how space weather affects you in radio communications. So yeah, of course, if you can do that in quiet times, then imagine what you can do when you are hearing actual space weather storm issues happening. You can absolutely hear these effects and how and if you understand what the phenomena that are occurring and how they affect your radio and how they affect the contacts and the bands, then you can absolutely diagnose exactly what's going on as it is happening in real time. So you are absolutely correct. Did not realize how much research has gone into GPS reception. Yes, there's a lot, and there's a lot more coming. Honestly, this is sadly, it's a field that's still in its infancy, and it infuriates me because this field should not be this far behind, because we've adopted GPS so much. I mean, we eat it for breakfast every single day. There are people who cannot get into their car without one of these because either they don't know where they're going or they don't know how long it's going to take them to get there because of the traffic, right? Uber, Lyft, people work with these all the time. It's not just people who are drilling oil who need the GPS guidance. People got to pick up their fare, right, using GPS-based, apps on their phone. It's become so ubiquitous in our daily lives that we don't even realize how integrated GPS is in our society, in the fabric of our society. So the fact that things like this can get disrupted is insane. Now, I haven't even gone in to talk about ADS-B. ADS-B is the new satellite-based platform for aircraft positioning. So it's basically GPS positioning for airlines now. And there are many areas that aren't even using, where they're trying to shut down all the secondary systems for GPS and just go to ADS-B so that they get all their GPS information from satellites instead of anything from the ground at all. And a lot of the emerging markets are moving that direction. A lot of emerging countries that are just getting enough money to be able to start having tourism and a lot of airlines, airline flights into their country. They are simply adopting ADS-B as the ground truth. And if you want to land in their airport, you have to be ADS-B enabled. So it's forcing a lot of the aviation industry to adopt ADS-B faster than they might want to. It's pushing the envelope. And that's a problem, because when the sun starts screaming again, we have no idea what's going to happen. We already have outages here and there, but if we get a global outage like we did back in 2006, imagine the difference. We didn't even have smartphones in 2006. We didn't have ADS-B and 2006, right? Imagine how much more disruptive it's going to be if the entire sunlit side of the Earth for hours on end gets no GPS. It's mind-boggling to me. So yes, we are doing more work when it comes to GPS, but we're still so far behind the curve. And there are countries in the world that don't even have a clue that there's a problem at all. You know, and I'm not even talking about the drones, right? We've got the drone industry to worry about as well. And nobody talks about that. Amazon Air has their drone facility located in Scotland. And I had a friend who, I had a satellite operator who did drones for fun, and he lives 30 miles from the Amazon Air drone facility. He was flying his own drone during a geomagnetic storm, and the drone under the aurora started making a banana carve out of the sky. And when we look back at the telemetry, the problem was it was losing lock on these satellites and then gaining lock on these, and so it would swing its position to match what those satellites were saying, and then it would lose the lock there because there was scintillation under the aurora, and it would regain the lock of these ones over here, and it would swing back over to get its position again. And so it just kept doing this, losing lock and gaining lock, and it just did this banana in the sky. But the banana was like 50 meters wide and like 30 meters high. Is that how you want a drone to deliver your package? Really? And yet that's what Amazon Air is doing. They are delivering packages to people in Scotland right now, in Aurora country, where you get twinkle twinkle little GPS. It's insanity. And they're using single frequency GPS, just like what you have on your cell phone. They're not even using dual frequency. They're not using high precision. Is anyone's mind blown yet? I hope so. I really hope so. Anyway, okay. So I need an underground bunker. Yeah. And we're not even talking about power outages. I'm not even talking about any of that. That's not what radio bursts do. Solar radio bursts do not do power outages. That's the geomagnetic storm that takes out the power. That's why Carrington events, people don't realize there's two parts of a Carrington event. There's the solar flare part and the radio burst part, and then there's the geomagnetic storm part that comes later. So it's a kind of a double whammy. Two different phenomena that end up causing two different types of issues. And the sun is capable of doing it all. So, and typically does it all at the same time, because these bad actors just fire. So anyway, let me now quickly check to see if we have some questions on Patreon. I'm going to jump over here and disappear out of view for just a moment. Let me see if anybody asked me any questions on Patreon. This is less something that people would probably ask a bunch of questions about, but rather be more, just enjoy the show. Yeah, it looks like we're good. I know Jerry Ryan is missing the presentation, which is too bad. And okay, so nothing there. I do know that I had a question earlier for Mike Richardson. You had asked, I don't know if I haven't seen you talking today, so I don't know if you made the presentation today, but he had asked a question about the 245 megahertz. Why are there always so many reports on 245 megahertz for the bands, and why is it that band frequency is so important? That's where a lot of aviation communication is being done. That's where a lot of broadcast television communication is being, transmissions are being done. There's also a lot of Air Force and government communications and transmissions being done on that particular frequency and in that particular frequency band. So that's why you see such an inordinate number of reports for that particular frequency range. And you can go in, and it is public knowledge, you can go in and take a look to see who actually transmits, who's actually allowed to transmit in that particular band. There's several bands in that range, and they're all restricted, but for obvious reasons, because of the services the government services that are provided on that. But that's one of the reasons why when you see these types of reports, typically at SWPC or in the NWS, they're required to give these reports, because the government needs to know whether or not their bands are usable that particular day. So that's why you see that a lot. And there are other issues too, but to answer that question, I want to make sure I got that question answered for him. So let me now go back and take a look to see if anybody has any other questions before I kind of close up our discussion today. Let's see, if I go back to the chat. Anybody have any other questions for me? Definitely put them out now. February 2021 is a deadline for ADS-B. And hey, Simplio, what do you mean the deadline for ADS-B? I know countries are adopting it all the time. ADS-B has been functioning for quite some time. I don't know about a deadline, so I'm curious what you mean by that. So if you could put that up, I'd appreciate it. Let's see. Yeah, you know, it's funny. People are talking about not airline, but truckers and whatnot. The sad thing is that a lot of people who actually drive trucks for a living, not just taxi drivers, and I get people who do that too, but a lot of the truckers, and I hadn't appreciated this, they're both amateur radio operators, CB operators, and GPS users, and they rely on this stuff far more than I had any clue about. And what actually got me to understand that was I was asked to do a Sirius XM radio interview for Free Reelin', which is a show that's all about trucking, and they specifically asked me to be on. Mainly for that, because it was going to really impact all the amateur radio and CB radio and GPS work that they did, and I got a real appreciation for how often these guys' rigs are really hit by space weather events. Whether it's a solar storm and they get scintillation from and they lose reception for GPS under the aurora, or they lose their ability to work their radios during all sorts of space weather events. So it's sad that there are these underserved communities that are of professionals that I never even considered being space weather susceptible, and yet you guys open my eyes every single day to new ways that space weather impacts our daily lives. So I really appreciate it when you guys step up and say, hey, what about us? It matters to us too. So yes, so thank you for making that comment about the truckers. Okay, let's see. I've been studying magnetic field for a while. There's a guy in England we sent all over the world to these magnetometers and muon detectors. That's cool. Muon detectors, I mean, we get a couple muon, I think it's about once every 2 seconds we get one muon pass through our bodies. Yeah, Thinker, thank you for your comment. All right, I'm going to slide down. I'm not seeing a bunch of questions here. Let me go back to the bottom. Okay, good. Let's see. Talk about bubbles in near space, please. You mean bubbles in the ionosphere? Archie, let me slide back to some of these questions here. My goodness, I got a lot of questions. Does science still reject God? I love that. Okay, I have to answer that one first. No, science never rejects God. The only thing you can do in science is prove what doesn't exist. Can we prove God doesn't exist? No. Therefore, you can't prove there's no God. That's scientific method, and anybody who tells you different is selling something. It's silly. It's silly, the idea that every scientist is an atheist. I actually know more God-fearing scientists than I know atheists. Just because Carl Sagan was an atheist and didn't like astrology or anything else like that doesn't mean the rest of us are just like him. I love Carl Sagan, but I think he missed the boat on certain things. There's so much that we don't know, and just because it looks like it's mumbo-jumbo, if you can't prove it is, then you have to be true to the whole edict of science. Scientists, you have a theory, you go to work to disprove the theory. If you can't disprove it, the theory stands. As far as I'm concerned, the theory of God still stands. Okay? Take your place wherever you want on that spectrum. Be an atheist if you want, be an agnostic if you want. I know a lot of agnostics who are scientists as well. I don't think it has to be mutually exclusive. I really don't. And you will never be able to pin me down to get me to say that I don't believe in God, because I don't think we have enough information to disprove. So why would I even bother? Okay. So that's probably as far as you're going to get me to go on the whole God thing. But no, science doesn't reject God, and please don't think that just because I'm a scientist I do, or that other people do, because that's just not fair. Anyway, okay. Do you go back and compare your forecast to actual events? Yeah, yes, I do sometimes. Space weather, as far as forecasting space weather, is such a gosh, it's just such a squishy, can I say squishy? It's such a squishy art that even if I get remotely close, I'm happy. We can't even get the Space Weather Prediction Center and NASA and ESA in their 3 different runs of the NLO model, for example, to come together and have exactly the same solution and say when a solar storm, for example, is going to hit. We even have the CCMC scoreboard where a bunch of scientists get together and make bets. It's almost like a betting pool with their particular analysis. When is this solar storm going to hit Earth? And I mean, there can be huge ranges in arrival time, for example. You can have a range where the differences will be 36 hours in arrival times. So squishy, very squishy. So if we get even remotely close, I'm happy. The biggest problem is that, of course, we don't have all the parameters. We can't run models fast enough, faster than real time. We have to simplify the models to even run them to get an answer that it would be considered a forecast. We can do forensics and get much, much better, but we can't run it ahead of time. And then on top of that, there's certain things we can't see yet. Magnetic field direction, for example, that's a problem. If we can't probe that, we can't probe the magnetic field on the sun very well. We can't probe the magnetic field direction in the big CMEs that cause storms. You know, there's a lot of things, a lot of elements that are yet missing in space weather. We are literally where terrestrial weather was back in the 1960s. And that's another reason why we need to raise awareness, is that the academic side of space weather is in its infancy. And if we ever hope to get better at doing forecasts and predictions, then we're going to need to make it more important. We're going to need to raise the priority on space weather and get more research and get more operational research done, where we're actually taking the events and not doing just forensics, but taking forecasting events and comparing it to real life and saying, is it working? Are we doing a good enough job? Where are we failing and why? And then make that a priority. And that field of operational space weather doesn't exist yet. We have the academic field and we have the operations. And we have something called research to operations and operations to research. And these fields, this is just kind of like some nebulous connection. But there isn't a designated field for that yet. And I think that field is going to come up through the ranks of meteorology, through terrestrial meteorology, because they understand weather. And space weather's not that different. And they understand the need that the public has for space weather. So this is what I am trying to create by doing exactly these types of things. So hopefully that answers that question. Okay. Your opinion of solar forcing on the climate. I will not even touch on climate science. It is incredibly hard. And it's very difficult. Will I talk about the forecast for solar cycle 25? How strong or weak might that be? And what should we prepare? Solar cycle 25, we believe, and I know you, Alan. Hi. Hi, Alan. Solar cycle 25, you know, we think it's going to be pretty much like solar cycle 24. It looks like we might start seeing activity right at the end of this year is when activity will begin to pick up. The official start of solar cycle 25 might not be until maybe the spring of the new year-ish. Between the spring and maybe summer at worst will be the official start. But the activity always picks up before the official start of the new cycle, what Scott McIntosh lovingly calls the terminator. So we think we might actually begin to see stuff pick up by the end of this year. We have been seeing solar cycle, sunspots from the new solar cycle already. We've been seeing them since 2016. As a matter of fact, there may be a new one rotating into Earth view here in the next few days. It's a high latitude sunspot cluster. Don't know if it's going to stay long enough as it rotates into view or if it's going to die out. But on the sun's backside, it sure looked like it was strong enough to be a sunspot. So we shall see if that's got the new polarity of sunspots, cycle 25. So that will be yet another indicator. And we are seeing more activity in the southern hemisphere than in the northern hemisphere, the new cycle activity, which is what has been predicted. Because we have an asymmetry right now. The northern hemisphere is kind of sluggish compared to the southern hemisphere. So that's part of the reason why the cycles are the activity is a bit low. But everything is kind of going the way we're expecting. So if our models and our predictions are correct, then yeah, by spring of this upcoming year, we could be into solar cycle 25. So let's keep our fingers crossed. Okay. What other questions do we have? Okay. It's there still, Tamitha. I missed what it is. What other questions here? Oh, right, space bubbles. Okay, again. Are you going to be, what is this, Tamitha? Are you going to be presenting or attending Observing the Frontier? No, I'm not exactly sure what even that is. Are there any plans to replace a solar telescope? You mean SOHO? Oh, God. Yes. What a heartbreaking thing. You know, SOHO is just limping along, and we just have not put a new solar telescope in place with a coronagraph. I mean, GOES keeps getting these. They look at SDO and think all we need are images of the sun, like SDO has. So they created, you know, SUVI, and that's great. That's great. But we don't have a coronagraph. We need a coronagraph. We have no if SOHO fails, we have no coronagraph. Without a coronagraph, we cannot get the speed of these coronal mass ejections coming towards us, especially as now stereo is beginning to rotate back Earth-side. You know, we'll be able to use their coronagraphs a little bit, but it's very frustrating. There are plans, but I don't know how far along they are right now. But we really need to replace SOHO. It's terrible. Now, the fully formed, the space bubbles. I don't know about space bubbles. I know about plasmoids and things like that, like coronal mass ejections and how they are handled, you know, what they look like in space. Are you talking about, if you're talking about ionospheric bubbles, plasma bubbles in the ionosphere causing scintillation and stuff like that, that's a hefty topic, and I might get into that later on. I still have yet to go through solar radio bursts. I mean, the second half of the solar radio burst examples with the Carrington events, and then I will go into solar radiation storms and coronal holes with fast wind, and I might do those both at the same time. I'm not sure, and then that will pretty much round out all the space weather phenomena, the series of space weather phenomena that I've been doing for these courses. After that, I might go into either the ionosphere. You know, we're talking about some of the details of the ionosphere, or go into the details of, let's say, the Earth's magnetic field, how it's changing, things like that. All of those topics are fodder for these mini courses, but it's going to be up to the mini course patrons what I end up tackling next. So and as a matter of fact, one of the strongest contenders is actually talking about the history of space weather, how it was created, where it falls in terms of terrestrial weather, and where the hits and misses were, and our stumbles and staggers during our, you know, rise to becoming a legitimate science, and where we have yet to go. So that would be a very interesting course as well. And I'd probably put in something about astrosociology as well, because it's such a large part of why space weather was created, and where it's going to go in the future. But those are things that I have to discuss with my patrons to find out really where their interests lie. So, okay, let's see. Any other questions? Just wondering if a full moon would amplify a solar storm. Might be a daft question, but I thought I'd ask. You know, if honestly, I'll tell you, if we were in Jupiter or Saturn, and our moon had an atmosphere and had a magnetic field inside it, like some of Saturn's and Jupiter's moons, yeah, it might actually do that, because then we'd get coupling between our magnetic shield and the magnetic shield of our moon, and there would be aurora footprints that would be connected. As a matter of fact, do I have, hang on, I might have a picture of it in this course. Let's see. As you can see, there's a lot of stuff I've got on these slides. I've got a lot of stuff that I haven't presented. That's for the next course. Oh, bummer, I don't have that slide with me. I was going to show you a picture of the Jovian magnetosphere. No, I don't have it. But you can actually see Jupiter's moon Io, as well as Callisto and Ganymede, the footprints in the Jovian atmosphere where the aurora was, and the magnetic field were connected. And so, yes, it could easily intensify. In our case, however, our moon is just a rock. It's got no atmosphere. Its big effect on Earth is its gravity, is its tides. The tidal effect is probably the bigger effect that our moon will have. So it most likely won't have much of an effect when it comes to solar storms. The big issue, of course, is when we get lunar bases on the moon, especially the southern pole, and we're going to have astronauts just sitting there, living on the moon potentially for a period of time. As the moon travels through our Earth's magnetic shield, basically in the tail, moon sits out. Its orbit is far enough out that it doesn't hit Earth's shield until it goes through the tail of the Earth's magnetic shield. Remember, Earth's magnetic shield kind of looks like a comet tail, or like a comet, and it kind of stretches out in the back. So the moon doesn't go through it in the front or on the sides, but then as it gets close to the back, then it penetrates the Earth's magnetic tail, magnetic shield, and then goes out and pops out the other side. And when it does that, that's going to be very interesting for these astronauts. I'm not sure any studies have ever even been done to see whether or not being inside the Earth's magnetosphere during a solar storm while being on the moon is something that's going to pose a problem, pose a risk for, I don't know, antennas or anything else that the colonists might, the lunar colonists might be, dealing with. Without an atmosphere on the moon, radio communications is going to have to be line of sight. They can't do any skip or bounce because there's no atmosphere. But radiation storms will hit the ground. So it could make the things very, very, astronauts very, very susceptible if there happens to be a big radiation storm that's hitting the Earth and causing all sorts of issues. There's all these complications that will be very interesting when we start getting to that level. But our space weather knowledge isn't there yet, so it's really hard to say. Okay, any other questions, guys? I probably missed a few, but okay. James Webb, for the James Webb telescope, they're seeing some kind of plasma bubbles. Sounds like an astronomical thing. I'm not sure. I've not heard of it, and that doesn't surprise me. Astronomy is a different field than what I'm in. Space weather is definitely a unique field, and so I don't always follow some of the scientific releases from astronomy. I'm still looking at all you guys talking to me. Ben also has a doctorate, just in a different field than Dr. Scove. Ben Davidson has a doctorate in what? Not physics, that's for sure. Okay, are we entering a new ice age? I don't think so. We're in a grand solar minimum, granted, but it's not. But a grand solar minimum, unlike all of the conspiracy theorists out there who say as soon as we hit a grand solar minimum, everything's going to, sunspots are going away, it's going to hit a Maunder minimum, everything's going to disappear for maybe 100 years. No, that's not what a grand solar minimum is. We just came out of a grand solar maximum. The grand solar minimum isn't much different. A grand solar maximum amplifies the solar cycle activity. So we get bigger, a larger number of sunspots. We get oftentimes larger events. And then a grand solar minimum weakens solar activity. So we get a less number of sunspots, a weaker magnetic fields, weaker events on average. But what works with the grand solar minimum and grand solar maximum is simply those hemispheric asymmetries, right? If you get both the northern hemisphere and the southern hemisphere magnetically in phase with one another, they're basically magnetically aligned with one another, you're in a grand maximum phase, most likely, because you're going to be getting amplification. You're going to get, they're going to work in concert, and the activity is amplified. They're both doing exactly the same thing at the same time. If they go out of phase, however, now they're no longer constructively interfering with one another. They're actually destructively interfering with one another. So what that does, there's two things that does. One, it weakens overall the strength of the magnetic field. If you have weaker magnetic field strength, you have less sunspots that pierce the surface because they're not buoyant, they don't merge through the surface as easily. If it's really intense, then no sunspots emerge, and that's what we had with Maunder, but that's an extreme case. Most likely not going to happen. But on average, you get weaker events. Okay, you get more penetration of cosmic rays because the sun's magnetic shield is overall weaker on average. But what you also get with the destructive interference, with the hemispheres being out of phase magnetically, is now the magnetic field is much more complicated because they're no longer simple structures on the sun. There's these complicated, weird things that are kind of scraggly. And now you can get really bad actors. So overall, you don't get as much activity. But when you get activity, especially during this, as we go down to the declining phase of the solar cycle and near solar minimum, you get these really bad actors, just like what we had in September 2017. You get, you know, what I showed, red, blue, red, right? That magnetically nasty, you know, 17-layer cake kind of combination. And you get all these magnetic fields that are pointing opposite directions all over, you know, in a really close proximity. What the NCAR team calls it is magnetic, hemispheric magnetic band compression. And you get because the hemispheres are out of phase, the magnetic fields are more complicated, and as such, you get these much more complicated sunspots that emerge, and they are far more reactive. They're far more unstable, and they can let loose these Carrington events without a problem. And as a matter of fact, this last solar cycle, as weak as it was, had 2, if not 3, Carrington-class events that were launched. One of them clipped us, as a matter of fact. It was during this 2017 event. The sun launched during one of the big flares, during that flare on September 10th. The sun launched a Carrington-class event that went kind of away from us, was actually shot tore away from Earth, like if I had a gun like this, and I'm aiming it this way. It shot launched this Carrington-class event out this way, and the thing was so wide that it actually clipped Earth. Could you imagine having a gun, the bullet is so wide that if I fire the gun here, part of the bullet still hits you? That's how big this Carrington-class event was. It also hit Mars. It was it let loose the biggest radiation storm that the Curiosity rover had seen in its entire history of being on the red planet. So, you know, these Carrington-class events do happen, and they happen typically in these weaker solar cycles. So you can say, oh, are we, you know, grand solar minimum, doom and gloom, you know, the sun is going to sleep. And it's like, well, not really. You know, the sun's just different. It doesn't mean it's going to sleep at all. It just means it's confused. It's arguing with itself. That's all it means. The sun is it's just arguing with itself, and the net effect is that the solar cycle is weaker but more complicated. And so, this is the problem that I have with people who think they know enough to be dangerous but not enough to be right. And so they cause these mass panics of what a grand solar minimum is. And you really need to, well, as they say, the devil is in the details. And you really need to look at the details when you look at space weather. And anybody who isn't doing that is not doing their due diligence and is being irresponsible. So hopefully that answers that question. Okay. But anyway, let's see. I'm going to see if there's anything else, guys. I think I'm pretty close to finished here. Let's see. I don't know if I see any others. Okay, we're still in an ice age. Well, I don't know. A Maunder-like event is bound to be repeated eventually. Yes, and this will be probably the last. Okay, last couple questions I have here. Yes, a Maunder event will likely occur before again. We've had deeper minimums than the Maunder. The Maunder is just the one that's in recent history when we actually had people looking at the sun. The Spore minimum, for example, was far deeper than the Maunder. The sun's magnetic field was incredibly weak at that time. I can't imagine what the cosmic ray penetration would have been at that time. My goodness, it would have been awful. And that's what I really worry about, is when the cosmic ray penetration ends up being, really intense, because we go into these minimums where the sun's overall magnetic field is very weak, and it can't shield out all the cosmic ray penetration. So then we get in these airplanes and we're getting, 4 and 5 CAT scans just traveling internationally. That's not cool. I mean, right now, pregnant women, I mean, if I were pregnant, I probably wouldn't fly. But that's just me. That's how I would use the information. I wouldn't want to fly right now overseas if I were pregnant, because I can get more, I can get 2/3 of the recommended annual dose in one flight. And that's not even a return trip, that's just one flight. So you return back and you're getting more, you're nailing your fetus with more than what is recommended for a pregnant woman just by flying overseas right now. And that's you know, that's kind of a scary thought. But you know, that's a different subject. But at any rate, so understand that there are other concerns when the sun goes into a grand solar minimum. There are other concerns other than just simply whether the sun has sunspots, right? Because there's a lot of other space weather out there than just simply coming, you know, the source being our star. So there was another question. I've seen a lot of other movement here. There was one question about amateur radio, about, I think, protecting radio equipment. I'm a ham in the Netherlands, PA20LD. I'm a ham in the Netherlands. What is the chance that we will be hit by a dangerous storm, and what can we do to protect our radio equipment? Yeah, the Netherlands. You can get some decent. Interference with radio because you're at reasonably high latitudes. The big issue that people have, and actually you and Francina, who is also from the Netherlands, might be able to talk if she's still online. She was online in the chat earlier. She's gotten shocked by her ham radio rig. I know people in Perth, Australia, who have been shocked during their during a solar storm. Most people who and this was with a G2 storm or higher. So a G1 storm, maybe not a big deal, but a G2 storm, definitely consider unplugging, right? Consider making sure your grounds are right, and definitely do not get up on your rig and start looking for problems. See, that is how people get hurt, is if they don't pay attention to space weather and they turn on their radios and they're getting static or they're not getting a signal, then they go outside and they climb up on their rig and they're not realizing a solar storm is happening, and then they get shocked because they're you know, so it's like, definitely don't climb on your rig during a solar storm. It's probably not a good idea. But I have had multiple incidences where people are getting shocked from their antennas during a solar storm, and I don't pretend to understand the physics. I would think that it's due to the fact that we have these huge fluctuations in magnetic field inducing current in the ground underneath you, and just very similar to the way power grids have issues. You induce currents on the ground, or in the ground beneath you, and that induces a potential in your antenna. And it may be, in some cases, large enough to shock you if you were to discharge it. So protect your gear. The best thing to do if you know there's a solar storm coming, ground your stuff, unplug your stuff, you know, just unplug your antenna. Keep it away from all your sensitive electronics, because there could definitely be potentials that could mess you up. I don't know what the conductivity of the ground is in the Netherlands, but like I said, I have firsthand experience or firsthand knowledge from a friend of mine who lives there, who did get shocked. So it tells me that there probably were ground-induced currents during the geomagnetic storms. But don't worry about solar radio bursts. That's not a geomagnetic storm. That's not when antennas have problems. They just can't hear. It's when the actual big solar storm hits Earth and causes aurora and all that other stuff. That's when you have problems with your actual antenna. Okay, and I think that's it, guys. Let me see if there's any other questions. Dreyfus minimum repeating soon. I don't know if we know really how to tell what kind of minimum is happening. I mean, there's a lot of mathematical models out there, but mathematical models are, you know, they're statistics based, and they don't. Oh, Francina, thank you. Yeah, it was during a G2 from my wire antenna. So see, there you go. So you guys might want to have an offline conversation about that, because it does happen. And Francina's in the Netherlands. I hope you don't mind me outing you, Francina, saying that where you live. But it's important. I think it's definitely important to take care of yourselves. But anyway, there are a lot of mathematical models when it comes to solar activity and when these minimums occur and that kind of thing. And there's a lot of different solutions. Zarkova, for example, thinks that we're not even going to come out of the solar minimum. And we'll see. We'll see very soon. But mathematical models make so many assumptions about things that it's hard to say if they're right. You know, we just the timeline and the time scale of the sun is so incredibly long compared to the timeline of human history, and also, of course, the timeline of the space age, that it's really, really difficult to make these really long baseline, you know, predictions with any fidelity at all. At least if you're being honest. Okay. Okay, guys. I believe you're welcome for the lesson. Thank you, August. And yes, hi, Francina. And yeah, too short-sighted. The mathematical models are too short-sighted. Okay. Was that the flare that was as big as Earth and was loaded with gold and nickel elements? I don't remember what the heavy ions were that hit. But pretty much every radiation storm, you know, if we get a solar energetic particle event, that's always going to have some level of high energy stuff, heavy ion content. Everything, and it's everything. It's everything on the periodic table. Whether we detect it all, we usually just pick out some that we detect. We don't always get them all, or sometimes the fluxes of particular elements are super low. But yeah, we get nickel, we get sulfur, we get iron, we get that in the normal solar wind too. I mean, as a matter of fact, that's some of the emission, you know, when you look at the SDO images, those emission lines that you're seeing are from things like iron. Some of these really heavy ions that when they get excited, energized, the emissions that they will give off from, let's say, sorry to go into chemistry for a second, but if you have an electron in an orbital, in part of that, it's promoted to a different orbit state. Depending upon the species of that atom that had that electron promoted, then you will get an emission of a particular frequency, and you know what that is. That's a spectral line, and you know what element that is, and you know what energy that is. You know all about it because we've done all these tests with, you know, chemistry and physics, and so we use these emission lines to be able to probe certain layers of the solar atmosphere. So these elements are in the sun and in the solar wind all the time, and we just get a bigger dose of them when when we have solar particle events. But the bigger dose doesn't mean you're going to start seeing metallic flake falling from the sky. It's nothing like that. It's not even close. This is still very vacuous. It's not going to be refilling our oceans or anything like that. So some of the ideas are pretty wacky. Otherwise, every planet in their solar system would have an ocean if that were the case. CMEs are they don't care which planet they hit; they just hit. So it'd be hard to refill Earth's oceans without creating oceans on other worlds, including our moon, right? So, anyway, enough of that. So. I think that's it, guys, and it looks like I'm saying good. I'm so glad you guys appreciate this class. I hope it hit home. I will tell you really quickly. We've now gone through all of the flare stuff. We've gone through radio emissions at Earth, and I have yet to go through the Carrington-class solar flares on 1959 and the 72. I will also hit on the solar flare myth. And talk a little bit about Hyder flares and why this has caused so much controversy and so much confusion in the public eye when it comes to what's a solar flare and what's a solar storm. Because some people used to think that solar storms couldn't happen without a solar flare, and we know that now, especially with stealth CMEs, that's not the case. And then we'll talk about planetary radio emissions and talk a little bit about Jupiter, which will be fun. And then we'll just do some implications and lingering questions, and that will be the course for next time. And then that will finish the radio burst, the solar flare and radio burst segment of our series, the portion of in our space weather basics, basically space weather phenomenology basics. So with that, I'm seeing lots of clapping. Thank you so much, and hearts. And again, thank you so much for the very, very engaging dialogue. I just love you all so much, and you make all of this happen. And so keep asking the good questions and ask the hard questions. I need them because it gets me to be more hopefully eloquent, if that's even appropriate to say. But it helps me be able to explain these things to you better, and it lets me know what works and what doesn't. So thanks again, all of you. Love you, and talk to you soon.